Anupam, sir.
Hello.
Good afternoon, sir.
Good afternoon. Good afternoon.
Sir, do you have audio video controls and screen sharing options enabled, right?
All are enabled. I think so.
Yes, sir.
Yeah.
Nice to meet you here.
Same here.
Okay, sir. So we'll wait for 50 more participants. Within 1 or 2 minutes, they'll join. 1 or 2 seconds.
Sure.
Okay, we'll wait. Okay, sir. Thank you. Good afternoon to all of you. On behalf of the Division of Artificial Intelligence and Machine Learning, Karunya Institute of Technology and Sciences, Coimbatore, I welcome all of you for ATAL FDP on quantum computing day 6 sessions. Today's sessions will run from 2 p.m. to 6:15 p.m. I have posted the agenda for each and every session. So we have two sessions, lecture sessions, followed by the test and then the valedictory function. After that, the attendance will be shared with you for this particular day. So there is only one attendance link will be shared at the end of day while you join for the valedictory function. So this is an instruction for you participants. Thank you, participants, for joining this session during your weekend or during your holidays. Many of you are joining from your college time, and some of you are having holidays. But in spite of your busy schedule, you all have joined. It's happy for us. So I hope these two sessions also will be useful for you. I would like to introduce the resource person for session one. He is Dr. Anupam Biswas from NIT Silchar, Assam. He completed his PhD in computer science and engineering from IIT BH Varanasi in 2017. He completed his MTech in computer science engineering from Motilal Nehru National Institute of Technology, Allahabad in 2013, and B from Jorati Engineering College, Assam, in the year 2011. Currently, he serves as an assistant professor in the Department of Computer Science and Engineering at National Institute of Technology, Silchar, Assam. Dr. Anupam has published several research papers in the reputed international journals, conferences, and book chapters. His research interests include machine learning, social networks, computational music, information retrieval, and evolutionary computation. He has successfully led two DST sponsored research projects as principal investigator in the fields of machine learning and evolutionary computation. At present, he is managing three sponsored research projects focused on AI and deep learning, quantum machine learning. Additionally, he has contributed as program chair, general chair for various international conferences. Also, he edited 9 books published under renowned Springer and Elsevier book series, and he has 7 patents. Also, he's having, when I have gone through his profile, sir, I hope you are having 1 crore plus funded projects. Dr. Anupam Biswas will be sharing his experience on today on the topic quantum machine learning for social network analysis. Welcome, sir. You may now take over the session.
Thanks for inviting, first of all,
Thank
and
you, sir.
thanks for nice introduction. Let me share my screen.
Sir, you can have discussion with the participants in the chat. Also, they'll post questions. And some of the participants, when they raise the hand, I'll unmute them and they can also talk to you. In between the session or end of the session, you can clarify your discussions.
Sure.
Thank you, sir. Thank you.
Is my screen visible?
Yes, sir, it is visible. You can go for slideshow, sir. Sir, I think the screen is not fit. You can just come back.
Okay.
Sir,
Is
can
it
you
okay?
just Fi key or slideshow? Slideshow, sir, slideshow?
Yes, yes, it is slideshow
It is
only.
in slideshow. The screen is not fit, sir, in our
Okay.
in the participant
So,
screen. So I think
what shall
normal
I do?
editing mode you can go, sir. Skip the okay, sir, fine.
This
This
is
is fine.
fine.
This is fine, sir. Is it
Okay.
comfortable for you?
Okay, somewhat, but presentation mode would have much better for me. Anyway, so I can continue with this, no problem.
Okay, sir. Okay.
If participants don't have any issue with this. Okay, shall I start?
Yes, sir. Yes, sir. Please proceed.
Okay, good afternoon to all. Namo Namaha. So, already 5 days sessions you have attended, and you might have already gained the knowledge about quantum computing, theoretical background, etc. So I'll be not going into the theoretical aspects. Rather, I'll be focusing on the application aspect. And application, as you can already see here, so we'll be discussing the social network analysis applications. Fine. So, so agenda for today's talk is as follows. So first of all, I'll start with why exactly social network is needed and what is the importance current scenario, current digital era, what is the need, why do we require social network analysis at the first place, and most importantly, why computer science people would be interested in social network analysis, right? And what kind of problems do we solve in social network analysis or in social network or social media. And lastly, I'll be now going into the quantum computing aspect, how we can leverage the quantum computing for various social network problems that we arise. Let's first look at why social network analysis is. I'll quickly go through some few snapshots of the news and articles that you already know social media, etc. So just to give you an in not insight, just intuition, why we are looking for social networks. So first of all, let's see. This is the news. Skip. You might have already seen this news. I mean, 5 years back, right? So if you can recall, so Trump's account is suspended. Twitter suspended that account, though it recovered later on. But the news you might have already heard. Another news you might have already heard about the Ladakh being presented in China map. So there was huge issue regarding that. Later on, Twitter Twitter apologized and finally corrected. And this is the recent one. So you might have already last year this happened. So Narendra Modi, our Prime Minister, just visited the Lakshadweep. So there was huge issue with this in Maldives. So you might already know. So what all these things? So these are related to politics, right? Or geopolitics, you can say. This is another news related to one social media platform called Parler. So this happened again in 2017 or 18. So there were some terrorist activities. So the users, some of the users of Parler social network actually involved in. Now, as a aftermath, so Google, Apple, Amazon, so they actually stop their services to Parler. The reason being why they stopped, because they find that they if they also caught into the issue, so they might have some business loss. So they therefore, although they were not directly involved in that, but they suspended the services. So the same period of time, 2021 or so, so there was news about the Signal. So Signal and the social networking platform. So WhatsApp being a little bit insecure. So that time this news was flashed. You can see Elon Musk also posted this particular news. And though nowadays these things doesn't matter, but nowadays WhatsApp is being still popular and people are using. Now what all these things actually are related to business or economy, you can say. Another thing, while I was searching this news about the Signal, etc. So what I noticed is, so these are the things you can see. This is the Silchar. So why Silchar? Because I was searching it from Silchar, and this is though I can say that I am from Silchar. That's why probably Silchar is being captured here. But here you can see this advertisement about the one refrigerator. Why it is being flashed? Because I was few days back, actually I was searching for refrigerators on Amazon. So probably they have caught this, and they have flashing this. They are flashing this news. I mean advertisement, right? So same advertisement in my Facebook profile also they were showing. They related to this refrigerator. Now what are all these things? These are called advertisement or targeted advertisement. Again, leading to the business or economy. Fine. Now that not only limited to that, so healthcare also nowadays you can see there are many groups in social network. They are posting the different related to different diseases, etc. There are discussions related to that. So health also are nowadays being discussed on social media, and people get health and benefit as well. Now, again, education is also not left out from the social media, today's social media. You can, most of you might have LinkedIn profile, ResearchGate profile, etc. Right? So, all these are related to education or research. So, overall, if we see, the social network nowadays plays a very important role. Uh, it relates to our uh, every activity that we perform, that associated with our daily activity. Right now, if we see as a whole, so if we don't have any account in social media, or if we are not active on social media, so we find that we actually, for people around us, we actually doesn't exist, right? So that's how the scene right now. Now the question is, why computer science people are interested in this? So though earlier this social network, the virtual media that we have, virtual social network that we have, so that were not there earlier, but uh, nowadays we have this online social media, so that's why people are getting interested in that. But why the computer science people are interested in it? Because when you see the users that are using, so they are generating different applications. I mean, they are generating huge amount of data. So every activity that user is performing, so they are generating data. Now for that we require efficient processing and different kind of analysis to perform the analysis, and how we manage all those data. So all these things require computer science people. That's why computer science people are involved in it. Now, what kind of problems exactly the in social network analysis we have? So there are many problems. But for today's talk and for the quantum applications, so I'll be discussing few of the problems which are relevant. For instance, community detection, link prediction, recommender system, influence maximization, information diffusion, rumor source identification or rumor detection, sentiment analysis, all these are very important, and they are uh, quantum computing may help us. Okay, so we'll briefly go into the different problems, and thereafter we'll see how we can leverage quantum computing in those problems. So first of all, we'll start with the community detection problem. So community, as the social network that we're saying, so social network basically is a graph, right? So all the problems, most of the problems will involve graph. Now, what exactly the community detection problem? While finding this group, so there are two conditions. So connectivity within the group should be very high, connectivity among the group should be very low. So which means that the people that we are forming the group, so they should be closer, and the groups among themselves should be dissimilar. Okay. So these are the two main objectives for community detection. Now, what kind of communities we identify? So communities can be divided into two categories: disjoint or disjoint or non-overlapping, and overlapped. So overlapped communities again can be divided into two categories: fuzzy or kissed overlaps. So here is an example. So this is disjoint communities. So disjoint means, so there will be no sharing of the membership. Okay. So when you say disjoint, so we mean that so membership will be attached to a specific group only. So whereas if we consider overlapped communities, membership will be shared. And again, as I said, overlap community, again, there are two categories. So if the membership is fractional, okay, membership itself is shared, then if it is not full membership, so then we'll refer those overlapping as fuzzy overlap. And if the membership is full, though membership may be shared between the groups, but if they are full, so in that case we'll be referring that as kiss overlap. So another problem arises, is called link prediction. So link prediction basically, if we have social media, whether there will be a link, future link, or whether any user, if the user is not active, so whether the links will disappear in future. So that's called link prediction. We have to predict which are the links that will disappear in future, or may appear in future. Then another problem arises related to rumor source. So often you see different kind of news, etc., are being shared. So who exactly the person who shared the news, or it may be uh, fake news. So in that case, we'll be referring that as rumor. So it, or maybe fake news. So but at the point is who shared it. Okay. So how do we identify who is the person who shared the news? So that is called rumor source detection problem. So basically, it's an optimization problem. So basically, we have to find the node which has the maximum uh, likelihood or maximum probability of being source of the news. Then recommendation in the social network. So you might have already seen in Facebook, in your Facebook profile. So sometimes these people, so who you might know. So this kind of recommendation you can find. So basically here again we just predict, just like link prediction problem. So we'll predict if there is a link. So for example here, so if I consider these two person. Okay, so whether these two, Henry and Bill, will be friend, so that will be predicting. So basically, this problem is referred as link. I mean, the recommendation. Okay, so basically, I will recommend Henry if there is a possible link between Henry and Bill. So basically, the link prediction problem again related to the recommendation. Okay, so we can apply both for finding the person who might be friend in future. So another kind of problem we have is called influence maximization problem. So basically, what this requires for the business houses who wants to advertise their product. Okay, they need to influence people so that they at the end they buy the product. Okay, so how they advertise is, so basically they target some users who are influential in the network. Okay, and they'll find that certain set of people. So if they target them and they get influenced, so in turn, so their friends may also get influenced. So basic problem is that to find set of nodes which by which we can cover entire network or maximum portion of the network. So that is called influence maximization problem. Now to this all this problem, how we are going, we can apply quantum computing. So there are very simple steps, 3 steps that will require to apply quantum computing to this. First of all these problems that we have seen, we can formulate this problem as optimization problem. So optimization problem means always to try to find best solution out of the possible or existing solutions that we have. So all the problems that we have discussed so far, starting with the community detection problem onwards till the influence maximization. So all these problems we can formulate as a optimization problem. And once we have the optimization problem in hand, so what we can do is we can map this optimization problem onto quantum computing domain. Okay, meaning the representation will be doing in terms of qubits, and then finally we'll apply a very famous algorithm that is called quantum approximation optimization algorithm. You might have already already aware of this algorithm because 5 days sessions already you are having. So we'll be looking at the prospects, how we can use this algorithm for these problems. To begin with, we'll start, because all these problems that we have seen will involve a graph. So we'll start with a very simple problem. So that is called max cut problem, and thereafter we'll try to apply into the one of the problem directly. So even if you don't know about these problems that I have discussed, so then also I suppose you already aware of the simple graph problems like max cut, min cut, etc. So to give you an indication, so basically in max cut problem, so what we do is we try to partition the network in such a way so that among this partition, the edges that are considered, which will partition the graph, will refer them as cut. So this cut, actually the number of edges in the cut should be maximum. So that is the problem. So first, for doing that, or to represent this problem, so we can formulate the optimization problem. Basically, what we have to find, we have to maximize the number of edges in the cut. So which we can formulate as this. So basically, if we see here, what exactly this is representing. So for instance, if I consider the level, the node level. So these are two node levels we have considered, -1 and +1. -1 means this is one set, and +1 means this is another set of node. So this line basically cuts this graph into two set of nodes having level -1 and +1. Okay. Now, if I just consider one pair, let's say consider these two pair. Okay, this node -1 +1. So -1 +1, if I consider here, so this value level will be -1, this one will be plus. So this -1 and +1 will give us -1, and this will give us 2. So therefore, basically this indicates that if we have two different levels and this edge, there is an edge between them, then this will lead us value 2. Okay, so therefore all such edges that will partition two separate labels of the node, so that will give us 2 for each of such edges. So therefore, for all such edges, if we count, so it will be counted twice. So therefore, here we have a half here. So this just halves the value, and at the end it gives the total number of edges that partitions the network. So this is the simple function, so that will give us the number of edges or cut that will partition the network into 2. And our objective is to maximize this number. So that's why you can see max as this term, okay, with level -1 and +1. Now, how we can use this objective function to utilize, how we can utilize this for in the quantum computer. Okay, so how we can do that? So basically, this is a classical representation that we have. So we have to map this into quantum domain. So for mapping it, what we'll be doing, it will be finding the characterizing Hamiltonian of C. So this is the cost function or objective function that we have. So we'll try to find the characterizing Hamiltonian, so which will be in a way representation in the quantum domain. So what is this Hamiltonian? So Hamiltonian is basically a diagonal with values on the diagonal corresponding to values of the objective function. Okay, so this is how it will look like. So all the functions that we have, function values. So if we want to find, say, for this particular function, so this particular function will set as 1. So likewise, for a specific function, if I want to get output, so we'll be setting that value as 1. So therefore, we'll have possibility, if I consider zeros and ones, so we'll have 2 to the power n number of possible. So this is this will be the representation for the classical representation into the quantum domain as a Hamiltonian. Now, if I consider the max cut objective that we have, so this we can represent in as a Hamiltonian as this. Now, how we are representing this? So here, basically, what we are doing is we are representing as a eigen value of the Pauli-G operator. Okay, so this Z is basically Pauli-G operator that we are using. So Pauli-G operator, the eigenvalues, +1 and -1. So our objective is here +1 and -1. So that that we have represented as a max cut objective. So in a classical computing, we are having -1 and +1, and if we have the eigenvalue for eigenvalue same as this, so we can easily represent that as a max cut or a Hamiltonian of that function. So therefore, we are representing it as Pauli gate operation. Now, end objective, what our end objective would be to get this quantity. Okay, so we have this cost function, and if we consider any specific bit, so that will lead to one specific function value, and finally we'll get that. And our end objective is to verify this whether it will be valid representation. We have to show that. So this function, if I consider, and we take the one qubit, and then if I consider this representation, okay, so whether we'll be getting the same outcome. Okay. So before going into that, let's just look at the Pauli operator, little bit working with this Pauli operator. So this is the Pauli operator, and as I said, the Pauli operator has eigenvalues -1 and +1. Okay. Now, if I apply Pauli operator to one bit with base state 0, so we'll be getting 0 here. If I apply 1, so we'll be getting -1 here. So if I just do this computation, we'll be getting 0 and 1. So -1, if we take out, so it will be qubit with base state 1. Now, here basically what we are observing is, if we apply this qubits on Pauli gate, so what we are getting is, if we generalize it, so if it will be -1 to the power x, so whatever value of x, if I consider 0 or 1, so we will be getting the result accordingly. So if I consider, say here 0, so it will be 1, so finally it will be 0 here, so we will be getting 0. If we consider 1, so we will be getting the value will be 1 here, so at the end we will be getting -1, and x value will be 1. So just by considering any value here, so we'll be getting, or we can say Pauli operator, if we apply to any bit, we will be getting this, like this. Outcome will be this. Then if I consider this for if I consider n number of bits and we want to apply it to ith bit, so in that case we'll consider Pauli on ith bit, and for rest of the thing we'll consider identity, and finally what we'll get is this. So for all the bits we'll have this, and specifically for that bit we'll have the -1 to the power that that value that we have. It will be either 0 or 1. Now, if I consider 2-bit, ith bit and jth bit, so same we'll have here. So these operations are tensor operations. So finally, we'll have x -1 to the power xi and -1 to the power xj for ith bit and jth bit, and we have this for all the bits, and specifically since we are looking for xi and xj, so we will have this operation over this. Now, moving back to the max cut with this background. So let us now consider the max cut operation that we had. So this is the max cut objective that we had, and we are having levels -1 and +1. Okay. And we want to represent in quantum domain, and we want to map it to quantum values. So now how we can do that? So basically we are reformulating using this. Okay. Now if I consider this xi, half of 1 minus xi, so xi we are replacing with this value. Okay. So or we can also consider the opposite way. So si we are replacing with, if I just rearrange it, we will get xi, some quantity we will get. Now if I just consider the levels here, so if I consider si value -1 here, so we'll be getting xi value 0. And then if I consider xi value -1, we'll be getting, so if we just apply here, we'll be getting 1 here. And if I consider the same for -1 to the power the xi value is 0 here, so again we'll be getting 1 and -1 here. Now it turns out that the zi operation, the Pauli operation that we have just now seen here, so here we are getting this representation in terms of x as 0 and 1, x as 0 and 1. And therefore, we can now represent this this as minus 1 to the power xi and minus 1 to the power zi, considering that levels now we are replacing as 0s and 1 instead of minus 1 and plus 1. And the objective remains same. Now the max cut objective, now we are having this, and we have the max cut Hamiltonian just now we have seen that. So this is the max cut Hamiltonian. Now to verify that, we have to show that. So if I consider this function of our specific bit x, q bit x, then it will get the same max cut objective that we have, and if we apply it to the same bit, that these two quantity will be same. So to verify that, let us try to apply this. So this is the Hamiltonian that we have, and then we apply it to the bit. So in this case, so we are considering 0 to n number of bits. So n number of bits we are applying, and then if we apply it, so just little bit of competition here. So this part identity matrix, if we just apply it to this, so this quantity will come here, and this quantity will be directly applied to these bits. Now this quantity that we have here, so we have already seen the replacement for this as minus 1 to the power xi, leading to the level 0 and 1. Now if I apply that here, and this quantity that we have, so if I just take a common, so now we have this part here, and we are applying to this. Now what is this quantity? So if you just look at this, so this is the max cut objective that we have. So finally we are getting the max cut objective here. So that means the representation that we have made is valid one. Now comes the role of quantum approximation algorithm. So quantum approximation algorithm, so I'll not go into the algorithm in detail. So basically, what we'll require is the parameterized state of the QA. Okay, so QA basically prepares this parameterized states, or sometimes also referred as ANS states. So here, what we have, so this is called this B is called mixer Hamiltonian, and this is called problem Hamiltonian. So basically, what we'll be doing is we'll be replacing this C with the problem Hamiltonian that we have, or the problem Hamiltonian that we have formulated for our objective, okay, which is max cut problem. So we'll be replacing this with the our cost function or cost operator, and this quantity is called mixer Hamiltonian. So you don't have to much bother about this, because this is part of generic QA over algorithm. So our part, our emphasis would be on this part. So that is related to problem Hamiltonian or cost operator. And because this one will not change for the objective that we will be considering, or specific problem, it will not change. Only this cost function will change. Now, after that, what we'll be doing after replacing, we'll use classical optimizer to optimize the two parameters. So we have two parameters here, beta and gamma. So beta is related to the mixer operator, and gamma is related to the cost operator. Now with this, let us now try to apply the quantum apply this to the community detection problem, which we will be referring as quantum community detection. So let us little bit get back into the objective of the community detection problem. What exactly is the objective of community detection problem? So basically, the main objective of community detection problem is to partition the network into two. Okay, so we have to partition the network into multiple groups, not specifically two. So but we'll be considering first of all we'll divide into two, then again we'll try to divide those groups into two. So basically we'll follow a hierarchical approach, but for this demonstration we'll be considering only two. only the top level will be considering, will not go into the lower level of partitioning. Okay, and the objective here is to just opposite to that of the max cut problem. Okay, so in a max cut problem, what we did, our objective is to divide the network such that the edges in the cut are maximum. Okay, but here in community detection problem, the objective is to divide the network such that the cut is minimum. So we can just consider opposite function for the community detection problem, considering the max cut problem. Okay, so just the opposite of the max cut will lead us to community detection objective. So therefore, the objective that we use just now for max cut problem, we can just replace this same objective, or use the same objective with the modification to this as minimization, as a minimization problem. Basically, the max cut was a maximization problem or optimization problem that we have. Our objective is to maximize that quantity, but here the objective would be to minimize this quantity. Otherwise, the objective function that we have seen so far is same. So whatever we have seen or applied to the max cut problem, we can apply it directly to min cut problem. Just the objective here will change. Now, how we are going to implement this into any simulator or real quantum computer? How we can implement it? So basically, three gates will be used. So one is Z, and X gate is also there in mixer operator, and then head-hammered gate. So this mainly these three gates will be used, and one rotation operator that will be used for this. Okay. To start with, let us consider the rotation operator. So what exactly this rotation operator does? So if you consider the block sphere, unit sphere that we have, so rotation operator just rotates the state of wherever it is currently pointing. So it will just rotate on the basis of the angle that is specified. Okay. Now the representation that we have for this is like this. So we can represent it like this. And here, so if you see the rotation operator, what exactly we do there? So basically, we will apply the complex exponential. So e to the power minus I, and then the angle that we have, half of that angle, and then if I want to apply it to z Pauli z operator, then we'll use z here. If we want to apply it to x, Pauli x or Pauli y, so accordingly we'll change it. And accordingly, so whatever state currently the Pauli G operator is having, so that state will rotate in the block sphere. Then if that is for simple Pauli G operator, if we apply on with a rotation operator, so that will be represented by this in the circuit. Then slightly more complicated, let's consider another G operator, Pauli G operator here. And if we apply that, so what will happen? So as you already know, the eigenvector for Pauli G operator is qubit G 0. Okay, so it means base state 0, and we have base state 1, and eigenvalues are 1 and -1. Okay, and if we consider this fact that if we consider exponential a, and we apply to any qubit, and then if it is equal to the some exponential of another quantity lambda, and we apply to the same qubit. So if these two quantities are equal, this will happen basically if we have a applied to the qubit v and lambda applied to qv. So if this happens, then this will also happen. So considering this, now let us try to explore or apply this to the operator that we have. So if we apply it to two qubits 0 0, so and we just try to replace this eigenvalue here with a G value here. So if I replace this for 0 0, we will have 1, because we are replacing this value we have already seen earlier cases. So we are replacing 0 with 1 and 1 with -1. So 0 0 we are having here, so we will replace with 1 1, and what we'll be getting is e to the power minus it. So if I replace with here, because we have 0 and 1, we will replace it with 1 and -1. So therefore at the end we will be getting e to the power it. So finally, for all these combinations, if we check, so what we are getting here, basically we are getting the value, so that is dependent on the parity. So if it is having even parity of zeros, it will remain as it is. Otherwise, it will have a phase shifting of phase. Okay. So phase factor is there. So if I apply it, so basically what we are getting, ei exponential of I z z t. So that will give us e to the power I z, then tensor product of z, and then t. So in generic form, if we write it, so for considering the same, if I write it in the generic form, so what we'll be getting is this phase factor, if we consider here, so -1 to the power a, this is the tensor product between a and b, 2 qubit that we have considered. So that will lead us to the phase factor. Now, how we will be representing it quantum circuit? So to represent that, so we'll consider 2 qubit a and b, and we'll apply, we'll just connect it here, and then we'll apply the rotation operator. So if I consider at this point, we'll have the cat operation, cat A, and we have the product of A and B, and then we have a cat operation again. And at this point, we have, if we apply the rotation operator, because the rotation operator, we have this quantity that will be applied here. And finally, at the end, again, we are applying the tensor product again with the quantity that we have. So finally, what we'll be getting is this. So e to the power -1 minus 1 a plus b t. So this is what we want to get, and this is the representation, circuit representation for this. Now, this circuit that we have that we have prepared here, so this actually will represent a particular edge. Okay, so and that edge, in that edge, since this one we are considering here as the cost Hamiltonian. Okay, so because the e to the power I z z t that we are considering here, so this actually you can apply the cost operator that we have, we can apply it directly, and finally what we'll have is, so this will be applied, you can imagine it is a kind of edge between two nodes, and if you consider representing the nodes as qubit, so then this linkage will represent that there is an edge between this, and we are applying our cost function that we have designed, we are applying that. This is what it will mean. Now, this thing we can concatenate, meaning we can apply multiple same operation we can apply, and if we do so, so this is what it will look like. So we are applying between I and j, we are applying this, and between j and k, we are applying this. So this basically means that if we graphically interpret it, so basically if we consider this as nodes, so ith node is connected to jth node, so which we are representing by this, and if we consider jth node is connected to k, so then we are representing by connecting this, and in between we are placing the rotation operator with Pauli gate. So likewise, if I want to have a connection between I and k, we can have another connection here. So now with this, we can easily apply our cost Hamiltonian or cost operator that we have, problem Hamiltonian that we have designed. So basically, this cost in the QA we have this quantity, right? So we'll be just replacing the C that we have designed for our problem, so which is this quantity. Okay, so we are just replacing this C here. And for mixer operator, here just the B is basically the applied to the Pauli X operator. So if we consider one specific term, so e to the power I minus xt. So how we can get this term, how we can represent this term? So let's start with the Pauli G operator that we have. Okay, e to the power minus I z t. So this is a normal rotation operator, right? So now if I expand it using Taylor's series, so this is what we will be getting. Okay. Now if I apply Hadamard gate or Hadamard gate prior to this and after this, okay. So basically we are sending this rotation operation in between two Hadamard gate. Okay, so if we do so, okay, so what we'll get is at the end we will be getting e to the power minus I xt. So one specific term means we want to represent one specific edge. Related to that, we have the cost operator for that. So for representing that, we can have two Hadamard gate, and in between we have the Pauli G operator. So basically the cost function that we have, so if I apply with Pauli G and then apply Hadamard both side, we will be getting the mixer operator finally. Now if I consider the mean cut problem that we have, and we want to represent for a graph, say let's say we have 5 nodes in the graph, okay, and we want to partition it on the basis of the objective function that we have designed. So we will be getting this like this. So here basically this edges as I have already told. So this circuit will represent that one node, that is Q0, is connected to Q3. So this is representing that Q0 is connected to Q3. Okay, again if I consider another pair, so here, so Q0 is connected to Q4. So like that, for every pair we'll have, pair means the edge in the graph. So because ultimately the problem that we have is in the form of graph, and we want to partition the nodes of the graph, and where the edges basically will be considering in the cut. So we have to maximize the number of edges. Okay, so that's why we are representing this as a edge. Okay, so finally we have the representation for the graph considering the objective function that we have considered designed for the problem. And then for mixer operator, so basically though here we are representing this with single, basically what we are doing here, this Hadamard gate, then Pauli G, and then H. Since we are getting at the end the rotation operation applied to X, Pauli X, so therefore here simply we are representing in the circuit as rotation over X. Okay. So finally, if I consider the objective, I mean the QoA objective that we had, so here they are basically the cost operator as well as the mixer operator, both were applied. So if I apply both this and this together, this is what it will look like. Okay. At the end, what we'll be doing is, so in between you can see X axis are also used here. Okay, so though it is little bit clumsy, so basically we are considering 5 nodes and we are applying both cost operator and mixer operator, and finally we are applying the measure. So because at the end we have to measure what are the states at the end after we run it for a specific number of shots. Okay, now here is an example how we'll be getting the output for the circuit that we have prepared. So for this, so basically these are the count how many times this particular string is being flashed, or that particular state, the quantum circuit that we have built, the circuits are. Okay, so 0 or 1 means, so 0 means one particular partition, 1 means another partition. Okay, color coded we can see here. Okay, so basically this count represents how many times this particular state is appearing. So if it is appearing many times or maximum times, so that will give us the result. So in this case, this is the result because we have run it for few shots only. Yeah, if we probably if we run it for 1,000 or more, so then we could get the better outcome. So which will lead us to better value or optimized value. Now for this certain small because simulation we can consider multiple, I mean qubits we can consider, but for real quantum computer it is limited and user access is not also available. So what we considered is we consider a simple small graphs for simulations and we try to find the partitions and try to find the communities from them. Okay, so these are the detail about the data set, small data sets that we considered. Okay, and these are the final results. So 3 partitions here. So why we have got 3 partitions here? So because we have specified that we want to get 3 partition at the end. As I said, first of all, the problem that we have designed it for 2 partitions because 2 levels we have considered. And second level again, what we did is we considered the same partition result and we try to partition it again 2. Okay, so basically this is a divisive approach. So we start with the entire network and we divide it into 2. Then again, if it is possible, then we'll try to divide it into again 2 or so and so on. Okay, depending on the need. Now this is what we are getting at the end. So after identifying the communities, so next is to evaluate these communities. Fine. So once we identify the community, how we are going to evaluate those communities. So there are different measures available for identifying, I mean, the evaluating communities, so which are categorized into 2 mainly. Quality measures, so which will emphasize or focus more on the number of connections, whereas accuracy measures on the levels of the node, actual level of the node. Yeah. So we'll go through some of the measures and later on we'll see how the results that we have obtained, what is the quality or accuracy of the community that we have obtained. So this is a very popular measure called modularity. So this basically gives us the quality of the community. If the modularity value is high, so which indicates that communities are of good quality, meaning the connectivity among the nodes in the communities are more, and if it is low, then it will indicate that the quality of the community are not good. So another measure we have isolability. So these measures basically tell us how much the communities that we have obtained are can isolate themselves from rest of the network. Okay, so I'll not go into the detail of the mathematical formulation, etc. So just give you an intuition that what exactly this measure actually does. Okay, so then we have adjusted RAND index, right? So here 2 things are required. One is the actual or the original levels of the communities, and then predicted one. Okay, so that's why as I said, the accuracy measure basically emphasized more on the level or level of the node, okay? Not on the connection among the nodes. Okay. So I'll just skip this part. So some examples I have given here. So let us consider these are the nodes that we have. So 12 nodes we consider, and we have the x levels, and that is the ground truth communities, and this is the predicted communities. Right. Now, if I consider pairwise, okay, how many times they are appearing same, okay, same in the same community. So xi and x1 and y1, if I consider, so this one x1 and y1. So y1, three levels are there, so three levels we will be considering here. So how many times predicted and ground truths are having same for that particular level? Okay, so that gives us this quantity. And finally, so whatever values we will be getting, we will be plotting directly into the ARI formula that we have. Okay. Then we have NMI. So NMI, again, another kind of accuracy measures. Here also two things are required. Accuracy measure, I mean the predicted one, and as well as ground truth one. So again, I'll be not going into the details. So examples, I'll just skip this. So another measure we have the parietal matrix. Just skip this. So directly we'll be moving to the result that we have obtained, and we will now see the results that we have obtained. So modulatory values for the community that we have obtained after applying the circuit that we have. So we have obtained modulatory value around 0.5. So though it is not that much encouraging because the maximum value is 1, but to some extent we got good quality communities. Then external density, so if it is low, so then it will be better. So you can see the communities that we have obtained, almost it is 0, and the coverage value we are getting maximum. And then accuracy measures. On accuracy ground, we can see levels are actually more or less better only because we are getting 0.7, 0.8 onwards. Measure we are getting 0.9, so which means that accuracy of the community are good, but though the quality is not that encouraging, but the accuracy of the community are good. That might be because of the network that we have considered, and that structure is as such that they are quality wise, if we see, they are not that much firm about the formation of groups. Now, to summarize what we have seen so far, so basically we started with the importance of the node. We have seen how important the social network is. Different problems we have, like community detection, link prediction, influence maximization. So where we can apply quantum computing, and how we can apply. So basically we can formulate this problem as an optimization problem. Then we map those problem, map the formulation of optimization objective into the quantum realm using the characterized Hamiltonian as a cost operator, and then we directly apply the quantum approximation optimization algorithm, QA, or simply QA-OA algorithm, that we can apply directly. And we have seen how we can apply that into one of the problem, community detection. Likewise, we can apply it to link prediction, influence maximization, or any other problem that we have seen so far. Or you can also explore some other problems as well following the same process. That's all from my side. Thanks for listening. So if you have any question, you may ask now.
Participants, if you have any doubts or you want to have a discussion, please initiate. You can press the raise hand button and unmute, or you can post your queries in the chat box. So there is
So
a
the
question.
chat box is not visible to me. How you can see
Okay,
that?
sir, I'll read the question. How can quantum computing improve the efficiency of community detection in large-scale social networks?
Large scale social network, it will not be possible because of the computation limitation right now we have, because the quantum circuits that we require, right? So as you have already seen how we are representing the circuits using the quantum, I mean the nodes as a qubit, right? So if I consider say n node, n number of bits will have, right? So if we have say billions of nodes, right, in the network, so which is because social network, Facebook network itself, you know, already we have billions of users, right? Now if I consider billions of nodes, so that representation will not be possible. So we have to think of an alternative way of representing so that we can overcome this kind of limitation.
Any other questions? Sir, there is a question. Can we use big data with quantum?
Yes, you can use. So, but that again depends on how you represent that. Okay. So if it is in terms of qubits, the data, I mean the scale is in terms of qubits, so then it will be not possible. But if you use alternative way of representing, then it is possible. You can do that.
Participants, any other questions do you have? Sir, I think there are no more questions.
Okay.
So one more question. How can quantum enhanced max cut optimization be applied in social network clustering? Quantum enhanced max cut optimization be applied in social network clustering.
As far as I know, so it doesn't enhance any, but because just to show the application. Okay. So there are many problems where actually it actually outperforms the classical computing. But here, just for the application we have shown, so this actually doesn't, I mean, lead to efficiency. Okay. Maybe this is because of the way we are implementing it.
Sir, one more question. How can Hamiltonian-based quantum models be used to optimize combinatorial problems like max cut and traveling salesman problem?
Yes, exactly that we have discussed. So all the process that we have shown here, right? So that's what I have shown. So this is max cut problem is also a combinatorial optimization problem only. Likewise, the traveling salesman problem. So if you can formulate the objective function, and if you can represent that in terms of the Pauli operation that we have seen as a cost operator, so then you can easily apply QoA.
Any other questions? Anybody want to interact with the resource person? If you want to talk, I'll enable your mic. Okay, sir, that's all.
Yeah. Okay.
Thank you, Anupam sir. We extend our heartfelt gratitude to Dr. Anupam Biswas for sharing his expertise on quantum machine learning for social network analysis. His insightful presentation has enriched us and understanding the evolving field, and deeply appreciate the time and effort you have taken for this session. Thank you, sir, for your valuable contributions.
Thank you. Thanks for inviting.
Thanks a lot. I'll be in touch with you, sir.
Sure, sure, sure. Okay.
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 Thank you.
Bye.
Thank you so much. Thanks a lot.
Bye.
Bye, sir. You can disconnect. Participants, the next session starts at 3:30. So 3:30 in the same link, kindly join. There are no feedback form now. The feedback form will be distributed only after the valedictory session. So kindly stay back. Ebenezer Jangam sir, do you have any other inputs? Thank you, participants. At present, the count is 200. Thanks a lot. 3:30, please kindly come and join for the session 2. Thank you. If you have any other doubts, you can post it in the chat. Test link will be enabled from 5 to 6 p.m. and you can join at the time here for noting down the link. After session 2 will be session exam. So kindly join here in the same link. Test link will not be sent to WhatsApp or to mail. Good evening, sir. Hari, sir.
Yes, good evening. Good evening.
Good evening, sir. Thank you for joining. Sir, I think your audio, video, and share option is enabled.
Yes, yes, yes.
Okay.
Just a minute. Give me a moment.
Okay, okay.
Yes, I think so. Share the screen.
Yes.
So,
Okay, sir. It is enabled. We can see your screen.
yes. And yes, and I think the video is also visual.
Yeah, yes, yes, sir. Yes, sir. Everything is clear. Sir, after a small introduction, we'll start.
Yes, so I think 3:29 is there, and after 2 4 minutes, we can start.
Okay, sir. Okay.
30 is already there anyway.
Ah,
Yeah.
yes, sir. Yes, sir. We can start this session. Participants are ready.
Yeah, please.
Good evening, everyone. On behalf of Division of Artificial Intelligence and Machine Learning, Carnegie Institute of Technology and Sciences, Coimbatore, I welcome all of you for the second session of Day 6 ATAL FDP on quantum computing. The resource person of today is Dr. Hari Prabhat from IIT BHU Varanasi. He's an associate professor in computer science and engineering. Previously, he worked as technical lead at Samsung R&D Bangalore. His research interests include IoT, ubiquitous computing, wireless sensor networks, human-computer interaction, and cybersecurity. He has published 35 IEEE transaction papers, authored 4 books, holds 3 patents, and released 4 open data sets. Dr. Gupta leads multiple funded projects, including work on federated learning, cybersecurity, LoRaWAN, quantum machine learning, and smart city application. He also plays a key administrative roles at IIT BHU, including head of the Center for Computing and Information Services and Chief Information Security Officer. Dr. Hari Prabhat Gupta will be discussing with us today on the topic Quantum Computing Toolkit with nuts and bolts of sack of tools. Welcome, sir. You may now take over the session.
Yeah, thank you. Thank you very much for organizing this event and invite me for the same. And of course, it is a very tough for an organization to organize such event, but definitely this is very helpful for the society as well as for the student and the faculty members. So thank you very much for once again organizing this wonderful program and inviting me for the same.
Thank you, sir. Thank you, sir. Sir, the audience can interact with you through the chat as well as if they raise their hand, I can unmute and they can also discuss with you. In between the session or end of the session, it's up to you, sir.
Sure, definitely.
Thank you, sir. Kindly take over. Thank you.
So in any participant, if you have any point, definitely you can raise in between. We will see and discuss and assume that this is a discussion session sort of thing, not some complete lecture and then after. No, that is not our goal. So let's start here. So as the title suggests that this is the nuts and bolts. So this lecture is a first step of the quantum computing, we can say, this presentation. And we assume that some of you are not aware about anything about the quantum computing. You heard the keyword quantum computing first time. So this lecture is at that level. Not for if you are already familiar with the quantum computing much advanced, then that is nothing to be useful. But yes, if very first time if you see that the quantum computing, then definitely I'm expecting that you find out at least some meaningful information in this session. So good afternoon to everyone. I am Dr. Hari Prabhat from IIT BHU Varanasi, and that is my research is smart sensing here and there. Say for example, sensing tiny machine learning as well as communication, wireless communication, and quantum machine learning direction. And today in this the talk, we will cover 3 sessions, 3 subsections. One is about the introduction about the quantum computing, then nuts and bolts, that what keywords is required for the quantum computing, and if you want to develop a program, how to develop a program, which platform is suitable, and that means what we need to pay the cost in terms of effort and other things with respect to the different platforms. So that is the third one. So here we have 3 points, that means focus on the 3 points. So today we all, that means quantum computing is very fascinating word. People are discussing about the quantum computing. That so it is not a new keyword. Is of course quite old, but still as a research point of view or as a terminology point of view, it's very new, and very few UG courses are there on quantum computing. UG PG courses are there. So but the principle is the same. That means whatever the physics book says in class 9 to class 11, that is the same principle. They follow the quantum computing. So indirectly we can say the principle is comes earlier, and right now people are using the quantum computing. So in principle, that is the quantum mechanics or mechanisms are using. And because since this is mechanics are there, so the quantum computing opens the domains or the research point of view domain as well as application point of view domain in all the directions. That is very much suitable for the physics department, much suitable for the metallurgy department, especially. They have the space. Quantum communication is for electrical electronics. Quantum computing machine learning is for computer science department. That means the quantum computing finds their applications and the research direction in all the domains, whatever the engineering branches are there. So this is the beauty of this quantum system, that everyone has some research space today itself, at least. Now, one question comes into the picture: why everyone say the quantum computing is the future, and almost all these companies, whatever the service provider companies are there, or whether that is data analytics companies are there, why they want to shift in the quantum computing? Even traditional computers or the supercomputers is already there. So that means India have numbers of supercomputers are there right now. Almost all these institute, IITs, and other things, they have their supercomputer machine, but still the quantum computing is required. So because they can solve the complex problem, that means they are not solvable, or if they're solvable, that means their time duration is quite long, and this time duration is not suitable for the real time systems. So in that case, the quantum computing is one of the best solution and example. So if you are familiar with, if you computer science, there are problems known as the NP hard or NP complete problems. Those they are solvable in polynomial time, or those they are not solvable in polynomial time. So we can't say the problem is not solvable, but yes, the problem solved in an infinite time or longer time in a traditional computer. But if we solve that problem in the quantum computer, then you can solve the problem in a very fast fashion, and all the with all the permutations and combinations. So this is the beauty of the quantum computing. They are parallelly, they are search the solution in all the dimensions, whatever the dimensions are possible. And yeah, this speed up the specific task compared to the regular computers. Because of the speed of the, especially in all the specific tasks as compared to the regular computer, so your task is also suitable for the quantum computing. That means we can't say the quantum computing is useful, or you can use the quantum computing in everywhere. No, the quantum computing is useful for a specific task. So say for example, if you want to sort a limited number of elements, then the quantum computing is nothing to be useful, better traditional computer. So every one problem, all the problems, we can't say the quantum computing is suitable or useful. But yes, of course, if the problem is too complex, then traditional computer takes time or not able to solve. The quantum computing is definitely they can solve the problem. And significantly advancement has been made in the quantum computing development in the recent years. So if you go to this source or information, physics and other literature, so you can easily find out that how fast quantum computing moves. It's very fast. So right now, that very few quantum machines are there, and the cost is very high because of their environment requirement is very high. But we expect that next 5 years, and that means in 29 28 29, most of multiple quantum machines are there. Companies are using that machines. Now we come to the complex problem versus small multiple problems. Yeah, please mute your mic. So the that means there is one side is hundreds of the computers, other side is one quantum computer. You know, so in that case, we can't say 100,000 or even more than that thousand computers can equivalent to the one quantum computer. No, there is no comparison between that means multiple computer, supercomputer versus one quantum. Their principle, their phenomena, their working culture is completely different as compared to traditional computer, even supercomputers or multiple supercomputers. Why? Because of they are searching within their one computer, others searching within their computer. Then after they merge their result and find out the final results, if possible. Otherwise, once again they do this heuristic again and again. Quantum computing, they solve the problem in all the dimensions at the same time. So we can't say the multiple computers, supercomputers can make a quantum computer. And this is because of this reason. Multiple unsolved problems in the past, now in the future, people are expecting that can solve. Uh, because of the speed, because of multiple searching options and other things. One a very good example is that suppose you go in the Make My Trip or some, that is the that means some ticket booking systems of the flight ticket bookings, or if you are if you find the path from Delhi to assume that you are going from Delhi to Chennai, and you are going via so Delhi to Mumbai, Mumbai to Chennai. Numbers of combinations are there. So usually traditional computer, they search within their domain and within a time period whatever the best combination they can solve, not all the combinations. So they can search only their research domain, their search domain, and find out a one combination they can solve. The time complexity is very high. But the quantum computing, they search in all the dimensions and everything. So their searching speed is very fast, and they are not miss anyone else. So they can give a best combination. So think about that. The tomorrow, all these Make My Trip, Yatra.com or IRCTC, all these portals, definitely they are demanding the quantum computing based servers, not the traditional servers, to solve their problems. Similar is face recognize systems. So recently, numbers of literatures comes into the picture. They use CNN algorithm or more complex deep learning, machine learning algorithms on the quantum computing to figure out the fast speed and better accuracy purpose. Earlier, if they take a more features, then how they can solve the problem in a given time period in a parallel fashion. Now it is possible. So the one thing is clear in our mind, that the quantum computing is not mean that the hundreds of the supercomputer. That is a completely different uh, phenomena and principles. Now, why such difference is there? Because of their from the scratch, their terminology or technology is different. So, if we talk about the quantum computing, they use the qubits as a binary. That means the smallest unit or the first unit of the quantum computing is the qubits, and which is that is the similar or comparable with the in the classical computer binary information 0 and 1. So, if you know about the 0 1 in the binary, the similar is the qubits in the quantum computing. But the quantum, they have the in between states also. That means they not only the 0 and 1, but from 0 to 1, or we can say some entitlement, some angle is there in between the 0 and 1. That is also the state or some or an element of the quantum computing. We can use as a state of that one. So in between the 0 and 1, hundreds of the states are possible based on their entitlement or based on their angle. So that is also we can use as a elements in that case. But here there is no element. So in other words, we can say if someone that is the system is the 2-bit system is there, that is the combination is possible only 0 0 0 1 1 0 1 1. Here in between the 0 and 1 is the numbers of states are possible. So think about that within 2 bits, how much number of combination, how much number of information we can process at the same time. So power increment is exponential. Why? Because of 0 and 1 and in between states raised to power. So because of the raised to power is exponential, here the linear power is increment. So if you add more 1 bit, then if 2-bit system 4 combination, if 3-bit system, that means the 8 combinations are there. But here that is goes the exponential. This is the beauty of the quantum computing and the quantum systems. Here we can see the classical bits are there. That is the 1, this is the 0, so 0 1 0 1. But here we can see, yeah, this intermediate states is also the state. That means that is also the information of the quantum computing. And this is the picture of 2020 up to the 2029. So we can see that if we talk about the 2019, that is only a very limited number of that is the revenue or investment, or we can say the quantum computing world size. So in that time, 90, suppose we 90 is a one unit. Right now in 25, that is the 70 90. So but if you see about the growth, that growth is so fast. So so within a, that means in a, even in a 6 7 years it reached 90 to 770. But 770 to 2500 is a very high growth is there in the quantum computing at that time. So this is the that means we can say that in the future is the quantum computing. If we see that, okay, this level of growth is going on. Even this report is 2020, but recently the papers or this the survey says that okay, the growth is so fast what people are expecting in the earlier days. So quantum is the future, and people are using in that case. Now, quantum computing, if we talk about the investment point of view, so that means one of the biggest investment done by, of course, the China. So China, that this report 2020, not 2025. 25 scenario is somehow different, but of course, increase or decrease. But we can say the China is, of course, investment 10 billion as compared to US 1.2, European 1.3, and India is 1.4 like this one. So the investment is going on. Companies are coming, they are fighting, they are on the same platform, they are working. So similar, if the investment is high, then definitely research space is high, and job opportunities are also high in that case. So, and we can see that almost all the companies, they have the quantum computer platforms. So quantum computing, you need a one platform, because the problem is that you are not able to purchase the quantum computer at your end. And as an institute, as a small size company, as a personal purpose, we are not able to purchase the quantum systems. So what option is there? These companies, they provide the platform, they have the quantum servers, quantum machines are there, and they give the credentials. You can use that credential with the help of that one, and then you can solve your problem on the quantum computing, because they provide the platforms. So IBM, Google, Microsoft, Intel, all these are working on the quantum, and they have their own platform. So all these companies, they have different platforms are there. So this is your choice in which platform you want to work, because once you start the working, say for example, IBM support this language for the quantum computing programming. Google supports a different type of the language for quantum computing. So it is very tough to shift from one to another. So it is good. You need to check the platform and start working in that up to the end. And investment in the India, that is, of course, some other companies are also comes into the picture, but there are two companies, they are very actively and filling the next couple of times, they invest huge investment. Their planning is next 5 to 10 years in this domain, the quantum computing domains. And of course, as we already seen that these companies, they try to invest, or they are working in this quantum computing, and how they can find out the futures in the quantum computing. This picture that we discussed earlier, told that okay, quantum find out the application in all the domain. Yes. So this picture also indicate the same thing, that cyber security. In the cyber security, the interesting thing is that quantum computing is helpful, or the quantum computing is a negative towards the cyber security. So right now, say for example, key combination. So you have the password of the a fixed length for size 5 size 10 size, and you have the, say for example, you have the limited time t is given for crack this password. Now the classical computer, they search the combination within a time t. Say for example, they search the 100 combinations in a time t. After time t, automatically the system shut down or lock because of your time is up. But 100 combinations are possible to try with the help of classical computer. But if the quantum computing comes into the picture, they can, within the time t, they can find out the thousands of thousand combinations, and all these they can try, and they can crack the key. So people are saying that right now no one evidence is available, and the calculation is going on that whatever the existing encryption and decryption algorithms are there, all these easily crack once the quantum computing comes into the picture. So now whatever we are using the password strategy, whatever we are using for encryption algorithm or mechanism, that is insufficient once the quantum computing comes into the picture. So say for example, if you have the encrypted PDF file, so encrypted PDF file requires some passwords. So you can put one password, okay, not working, two password, three password. How much password you can generate with the help of classical computer? To hundreds, 200, 500. But quantum computing, within the time limit, they can find out a huge number of passwords, and they can try that things. So your 4-digit, 5-digit PDF encryption is nothing to be sufficient when the quantum computing comes into the picture. So of course, pros and cons are there. Similar is the information communication. So if you use the quantum computing, then your information communication is so fast. So quantum communication is very fast. So that means easily you can broadcast positive or negative information within a time domain. And this is the also battery management and weather forecast. So how it is helpful in the weather forecast or the traffic and other things? So this satellite data size is very big. The problem is that within a second they send a huge GB data is there. That means if you consider all type of information, then very bigger size data is there in the weather forecast. And with the because of these all these supercomputer, most of the supercomputers people are using the data set of the weather forecast and other things. The data size is very big, and parallelly we need to solve the problem. Otherwise wing speed is in this direction and temperature in that direction, how we can predict that okay whether rain is there or not? So if raining is there, the wing speed and the temperature of or an air pressure of this environment is important. So all these factors work together, then after you can predict the weather. So weather forecasting is possible. But once you consider all these dimensions of the data set, then it takes time in the classical computer. But when the quantum computing comes into the picture, within a time period, you can easily predict the weather, because you can compile, you can process all the information in a very short period of time. Similar is the traffic, solar, and clean, and other financial. Okay, financial department also, that is once the quantum is there, you can very easily predict the stock market and other things once the data set is very big in that case. Medical science, DNA problems and DNA structures problem is there, and this is still that is NP in a complete NP hard. So because it takes huge time and no solution is there that in that case. So if such a high processing artificial intelligence comes into the picture with the help of quantum computing, definitely it will be very helpful. So all these things motivate us to work in the quantum computing. And whatever the directions you are working, you need to work in the direction with the help of quantum computing. And we are not required to change our direction, only need to change the platform, that whether we use the classical or the quantum computing. Now this is that is the this picture indicates the practical outcomes, this bottom line blue color. So this is in the market, that these devices are available in the market, not the philosopher things, or that means on the concept point of view. So this type of the chips are already available in the market, and they are designing with the help of the different companies, especially IBM and Quantum. They mainly focus on this direction, and they successfully deliver all these uh, chips or the quantum computers. That is, quantum computer controllers are there. They have already developed. So whenever we see that okay, one company is working, so uh, they design the systems first. Then after they design the kernels. So circuits and the Qiskit and Qiskit library and Qiskits designed by the IBM. So these are the developers are there, kernel developers are there, and above than that one the algorithm is there. Quantum algorithms, application model, machine learning, natural algorithms, and optimization. Along with that, the quantum services and other things are also integrated. And top on that one, the prototype of the quantum service applications and other things. One thing is very interesting, that suppose you want to work on the quantum computing, there are two options are there. One is that you can work on the hardware itself. That means you can create a user ID password account on the IBM platform on the quantum, and access some machine, take some credentials and access some machine. Indian government also start the quantum in cohort 1, 2, 3, and so on. So in that they have given the free of cost the quantum space on the Cisco platform. So maybe possible someone of you, maybe possible someone is interested. So you need to explore the quantum computing cohort DST, and they provide the free of cost. So here in that case, if we have the credential, we can use these machines. Suppose you have no hardware, no account is there. That means you have no credentials. Credentials are not available. Then you need to work in this platform. This platform is also, this is the simulator sort of thing, but not the simulator. This is really a developer, and you can develop your program at this level, and you can test whatever you are doing. So you are not worried about that whether machine is there or not. No. You can find out the same program, same algorithm, everything is there. Algorithm designing and other. So up to 2022, IBM focus on the algorithm designing and other things, not the quantum prototype quantum solution applications. So once the algorithm is settled down, that this algorithm is working perfectly, they can solve this problem without any bug and other things. Then after this, so here right now we already have multiple models are there. So say for example, quantum computing based algorithm, machine learning algorithm for face recognition. You easily find out the models and other things. So you are not worried about that whether the library is there or not, toolkit is there or not. So all these things are ready after 2023. So right now we are not required to start from the scratch and other things. Already work is there. And this. In this picture, some other interesting fact is that when they start working on the 2019, you can see the 27 qubit machine is only there. So a very small size of system as compared to 2023 24 comes into the picture. So that is the first that build that means the ready system model is 27 qubit only. Then after the jump to 65, then 127, then 433, then 1012. After 1000 qubits on the single chip, the problem comes into the picture. Problem in the sense that means how to control whether it is completely useful or not. Maybe possible they are not using complete, and someone is locked because of their task is there, and others are not able to run that thing. So to improve the accuracy, to improve that complexity, they suggest that okay, like this type of architecture. That means break down this one, but of course the size is 1 1 1 2 1. That means they connected multiple, but this connection is not like one is here, other one is there connected. No, they are internally connected with each other and make the 1 1 2 1, so that, this delay is theoretically it's zero, and they are connected with each other. Similar as they increase the size. Once they increase the size, they tested it and they find out that it is not possible on the one chip. That is 1 1 2 1 is itself is quite complex, and they design, propose, market, and then after they do like this type of exercise. So in the future, they start that means the section or subsection sort of thing combination. So now they design like this one and this. The difference from this solution and that solution is that here two, that means parallel connections are there. That means you are not required every time to go from this to this to this to that. A to B and B to C is not required. A to C directly is possible, but here this type of combinations are there. So such differences they have done and find out some good results and good solution like this time. So once right now people are not that means worried about the future about the quantum. Why? Because they assume that and they're 100% sure that okay, someday definitely after some years we find out a high qubits machines, that is 10K to 100K qubit machine. Why? Because such architectures are quite stable and find out this structure. This type of, if we they focus all the qubits on the same chipset or same, then it is not possible. Right now, once 1 to 2, 2 to 3 connections are possible, then it's possible. So this is all about the IBM roadmap, and right now we are in 2025. So this is the picture, and that is. So now applications are ready. Corresponding the application, machine learning, natural language or natural sciences, or the optimizations algorithms are ready on this IBM platform. You can directly access and use that one. And quantum service less, this intelligent architectures and other things, circuit library, circuit libraries are ready, and these platforms are tested and ready for the use purpose. These are the domains that is there in which direction that these domains are working. So quantum computers, ultra fast and efficient solutions, and that means quantum computer. So the main purpose is to solve the problem as soon as possible in the quantum computer. If you are using the quantum computer direction research, then their main objective is to fast algorithm, deep learning algorithm, machine learning algorithm. So that is the quantum machine learning. Speed is the main play the role in that case. Quantum communication directions. Right now, the research is going on towards the security, cryptography, transmission of the information, how securely transmit, how securely we can encrypt, and other things. So the quantum computing direction. If we talk about the quantum sensors control and methodology directions, so they have some physics principle or in terms of the sensing in that case. So that we can that means read the environment as soon as possible in the correct time. Quantum material size direction, that they focus on the designing the material for the quantum computer, that of course in a small level, then after they go up, so that this material can support a large number of qubits in the system like this. So this is all about that means we can say the market survey or what's going on in the quantum computing. Now we come to the some keywords of the or the principle of the quantum mechanics, or say the quantum computing, which principle they are using. So there are two things are there. One is the superposition, other one is the interference. So superposition, two or more quantum states can be superimposed to create the another valid quantum state. So similar as this is a binary in the classical computer, 0 and 1 is there, then after they find out the result. Here qubits are there. So how qubits can design? Qubits design with the help of 2 bits. 2 bit is there, but this is not like the 0 1. That means the qubits are there and they can form the this one. And they have some entitlement or angle is there. So with the help of angle, we find out more positions in that case, and inference is the same as the result that if the opposite side of these bits are mixed to each other, then that means they destroy the information and destructures the information. And constructive way that they are working in the same direction, then you can find out the better position or better. So this is the physics principle says that. So if we want to destructure and finish that state, definitely we need to generate the reverse direction of the force in that case. Entanglement says that that means the groups are two or more particles, they are the quantum state, each cannot be described independently. That means they are connected with each other. So that if something is happening in the one, then definitely the effect on the others. You can't say they are the completely independent. So that is that means the main fundamental of the quantum communication. So something is happen here, then definitely the impact is on that one. So it is not possible they are completely independent with each other. This is the entanglement in between this group of two or more particles. They are connected with each other. If something is happens with the one, then definitely other impacted with that one. So, and because of that reason, the quantum computing is processing parallelly, because whatever is happening here, then all these things are doing the same thing, or they are also affected. So parallel and other controls are possible in that case. And quantum communication comes because of only this thing. If one is affected, then other, and how one makes the previous slides. So with the help of this, you can make the qubits. One qubit they can measure with the others one connected. Other very important thing is that quantum state you are not able to measure. If you are not measure, you are not measure that state, that is the quantum. If you try to measure that state, then this is a classical. So say for example, if you have some, that means if you have one coin is there is one head or tail is there. So you have 1 rupees coin is there. You can just flip this coin in the air. That is either head comes or tail comes into the picture. So if you want to see, if you want to measure whether what state is there, that is the state is head or tail. How we can find out? The coin is either in your hand or at the surface. But whatever in between, when the coin is in the air, what states are there, you are not able to measure. And when you try to measure that state, whether this is the head or tail, that means that is not a quantum. They are not flipping in the air. You see that, okay, this is head or tail. So similar is the quantum. If quantum state can survive only up to when you are not measuring. If you try to measure, then this is not a quantum. They convert into the classical bits. So this is the main advantage of the quantum. You find out various states only with the help of two. But this is also little bit challenge to maintain their states. So say for example, one hardware, one quantum material, they required this level of temperature for maintaining this state. Otherwise, they lost their property and convert into the classical. So that means there, whatever the physics or whatever the material required, you need to provide that level of support to that machine. Otherwise, you are not able to find out that type of the results. Since this information or this quantum states are not able to measurable, that means you are not able to measure or not able to observe that things. So you are not able to store or recreate. Okay, so whatever is there, that is in air. You are not able to measure. You are not able to. That means observe. So in that case, you are not able to store that information. If you try to store, that means you are measure. If you measure, then that is not a quantum. Since you are not able to store that information, you are not able to recreate that because you don't know what is the information. So how we can recreate that information? And this is the main reason that in the quantum machine learning, back propagation creates the problem. Because in the classical machine learning, say for example, that is the one layers to another layers to another layer. Some weights are there, you move it. Then that is the gradient comes into the picture. Gradient says that no, this is not a good accuracy. You can go the back propagation, but for the back propagation purpose, you need to store, you need to recreate that things. So that type of challenges are there. So these three things are important in the quantum, and they follow. One is that the entanglement, that means whatever happening here that also affected the others. You can't measure the state, you can't measure the quantum qubits. The third one is that you can't repeat or replace or store the quantum information. Now, numbers of times we say that this is the similar as the bits or the qubit, but if very first person they say the first time in the quantum. So what is the qubit? So qubit is of course the bit in the classical computer 0 and 1, but they also have the entitlement. That means they also have the angle information in terms of alpha and beta. Okay, so assume that this there is one plane is there in 3 dimension, x, y, and z is there, and 0 on the z plane and 1 in the x and y plane. So whatever the angles in between is, we can say with the help of alpha and beta, we can figure out. So this is that Albert Space principle says that okay, you are in between the 0 and 1, and an infinite direction like this one, 2 dimension complex plane is there. So now we clear that okay, we classical computer 0 1 we can easily convert into the we can easily compare with the quantum bit, which is the qubits, and they have some angle alpha. And with the help of angle, you can find out the alpha and beta in that case. Now, how quantum process, that means suppose you have the binary information. So what we can do, and then the next step, how we can perform the operations. So operations performance with the help of gates. So logic gates are there in this our digital that and or not gates are there like this one. So quantum also support that type of gates. So if they want to perform the operation or they want to reverse the information, they want to change the information values, they perform some gates. So so these numbers of gates are there. These are the example of two gates. So and they helps to change the state as well as they help to change their values. That means they help to change their angle as well as their values in that case. And one beauty or one uniqueness of the gate is that they are reversible. That means whatever you are doing, again gate, you can find out the original information. So reversible is possible. You can reverse whatever you have done with the help on the data with the help of the gate operations. You can reverse that one. Every one these gates are quite common and very useful. X gate. So suppose in the deep learning or machine learning, if you want to perform some operations, as say for example, you want to multiply the data, multiply the weight of neurons A to B. So here you need to use the gate, and there we use the arithmetical operation like this one for the same purpose. So this X gate says that that means the reverse or flip gate, and a bit flip gate is there. So original information is alpha, 0 is here, 1 is here, and this is alpha and this is beta. In X gate, beta comes here and alpha comes here. That means this is the bit flip gate is there. They just flip the information of the bit in that case. Z gate is the phase flipping. That means here that is the positive and now negative. The values are not there. That means that this is in the just opposite direction. Then we can use the minus. So in that case, we can say Z gate in that case. And how we can find out very easily. You just need to multiply the values, whatever the values are there. You can very easily to find out the gates. So this is the pictorial diagram of that one. So X gate, what they are doing, alpha to beta, beta to alpha. So they rotate towards 180 degree, and earlier that is the angle is this one, now the angle is like this one. So alpha and beta just swap. So some people they also say the mirror gate like this one. So just flip the values in this. So it helps to perform all the operations. So that means with the help of these gates, we can perform whatever the operations are required with the data. So for the operation with the data, we need to use the gates. So Z gate is also, as we see that okay, they flip the that phase flipping is there. So this is the given phase. Now, if you want a reverse phase, you need to use the Z gate. So the phase, but this the values are the same, alpha with the this one and beta with that one. So they are not changing. They are not playing the with the values and game with the values. The values are the same. HGAT change the values in terms of square root. And so HGAT required when you want to change the values in terms of the square root. So then you need to use the HGAT. And this is the summary, or this is the that all other possible gates. So numbers of gates are there. Here we cover some gates. So say for example, this is the unary, only one input is there. These are the one input. These are the two inputs are there. So two cross two dimensions are there. So that means it depends on the input, what type of operations you are required, what type of operation you are doing, and based on that one you can select the gates. Suppose we are aware about the gates, we are also aware about our information 0, 1, alpha and beta. That means how we can make the quantum circuits. Similar as in the machine learning or deep learning circuits are there. So quantum, they have the circuit. That means they want to play with the information. Multiple states are there. First state, they are doing this one. The outcome of the first state goes to the next state, and then they are doing some operations like this one or something like that. So these are the that means the states are there in that. So suppose these are the inputs. Your input is 0 0 0 0 with the some alpha and betas, and I want some output required. So what we will do, we perform some operations. How we can perform the operation in the quantum? With the help of gates. And at the same at a state they use one gate. Now the second state they use the next gate, then after next gate, like this one. So these are the gates are there, and they play with the game. So here we can say that qubit 0 line, the first line, they are not, there is no gate is there. That means the original information is as it is. The first line, they perform the first one gate at the stage 1, and then after the same thing is there. So they perform only one gate operation here. The second is also one, and the third one, line number 3, they perform the two gates operation. That means first, after first, they find out some information, and with the on that information, they once again they use the gate and find out the result in that case. Now assume that you familiar with the qubits, you familiar with the gate, you also familiar with the circuit. So this circuit is on your paper, not on the your tool or the computer. So how we can write this circuit on the computer programming? So this is a program for this one purpose, that you need to write on Qiskets and other things platform, but the programming platforms are there, and you can see your results and other things. So here very first you need to write the initialize whatever the that means the qubit informations are there. So this is 0 1 2 3. Then after you need to perform the gates operations. So step 1, this there are 3 gates are there, you need to perform like this one. In the step 2, you need to perform the second level of the operations, whatever operations are there. So they automatically work in the sequential and solve the your problem. Now this picture is the complete picture of the that means computer architecture sort of things, not only the quantum computing. So how this architecture works, quantum computer architecture works. So very first, say for example, you have a one MATLAB software. So this is your software and your data is there. Your classical computer solve that problem or collect the data, whatever they are doing at their end. They perform that one, and then after they they transfer this result to the quantum processor or quantum chipset. So assume that the quantum chipset, they have that that means the input from the classical computer in a different uh, presentation. So that the quantum chipset can understand whatever the input is there. Then they perform the gate operations, whatever the gates we have seen that, and after that they connect as a state 1, state 2, state 3, like this one, and solve your problem. Once your problem is solved, then the measurement comes into the picture. Very interesting, measurement comes into the picture. That means now they lost their quantum property at this level. Okay, because now we try to convert the quantum to the classical. So of course here we are going in this way. Quantum gates or logic circuit, they convert your information into the quantum circuits, and at the quantum circuit the result is there. The result is the measurement. So they convert quantum to the classical, and whatever the classical result is there, so the classical computer, because classical computer is not able to do that thing. So at the quantum chipset they need to do that things. So similar as that is the one gateway is there. They have one demodulator. Whatever the signals come, say for example, you have the Wi-Fi radio. So whatever the input comes into the picture, they need to use the demodulator, understand the information, do the operation, and once again modulate that information. Like the same thing is here. Classical information comes into the picture, convert into the quantum information with the help of gates, perform the operation, and then once again convert into the classical information, the same information. Now, whatever the architecture that in the previous slide we have seen, if we try to break down that architecture, we easily find out the 5-layer architecture. Okay, if we have these 5 layers, we can easily work on the quantum computer. So similar as in this networking, that multiple layers are there, multiple, that the same thing is here. But these layers are that means somehow we can say the theoretical of philosophers. So if you go to the architecture, quantum computer architecture, or if you go to the quantum computer and open that one and search where is this layer and what, no, that is not there. This layer is with respect to their duties and the responsibility, not with respect to their implementation. Implementation may be possible one common package for all. So we can't say this clear classification of the layers of the quantum architecture you can find out in the system. No, that is not there. So these are the layers. So very bottom comes on the physical layer, which is directly connected with the hardware of the quantum. There are the physical qubits or chipset is there. Then after the physical layer, that the information is detected, then visualization comes into the picture, information processing. Okay. They are not that information representation and information processing on that one. So they are not doing any logical operations. Okay, they just try to understand what information is there. If any conversion is required, they can do that things at this level. Quantum is very that quantum computing is very sophisticated, that errors comes very frequently, because all these things are doing on the hardware, and hardware itself has the noise. They work on the physics principle. Hardware also works on the physics principle. So in that case, if any minor error or minor noise is there, that is also impacted quantum, because of they also follow the physics principle. So that is the error correctness. So you need to handle the errors at their level, so that you can implement the logic successfully. Otherwise, you can't implement the logic successfully if you are not able to handle the errors in that case. Then after logical communication, logics comes into the picture, that we have seen that this one. So if you want to merge this result, that logics comes into the picture at this level. Then application quantum algorithm comes into the picture, whatever the algorithm, and they show the result, or they forward this information to the end user once again. So this physical layer or the hardware comes into the picture, starting from this way and that way and up to that one way. So from this state, whatever the black box is there, if we open that black box, we can find out the 5-layer architectures. In summary, if we can do like this one, the physics layer, it consists of the physical component that is encoder with implement to the actual qubits and their operations. So whatever the chipset is there, all these things comes on the physical layer. They are talking about the physical components of the quantum circuits. And uh, virtualizations and other things layers, they actual quantum state to information, such as qubit and physics operation to the logical operation gets. They can convert, they visualize how the information gets visualized, and how we can virtualize that information, because this is the physical, and this is somehow hardware, this is somehow software, some intermediate layers is required. It work as a intermediate layer. Error correctness layer responsible, and they implement the error correctness mechanism to create the noise-free logical qubits. Because error comes at this level, error comes at that one level, or if this information transmit with the help of quantum communication, then that is also wireless. So that is also create some errors or noise. So all these things are take care at the layer of the error correctness, and their objective is to generate or to create a noise-free logical qubits. Then logical layer comes into the picture here. They provide some logics, whatever operations you want to perform, where you want to perform, and finally you can see your result at this platform. Now, quantum computing paradox, if we talk about that, all these companies, they are working in this direction, and they gives their own platform to solve the quantum computing problem. And and here we can say yes, some unitary metrics or bimetrics are also. That means numbers of type of the gates are there. We can't say that the gate takes only one input or gate takes on three inputs. No, that is multiple possibilities and opportunities are there in that case. Now we compare with these the computer algorithm subject, that is the P, NP, NP complete, NP hard problems. Similar as the quantum, uh, they also okay. Yeah, similar in the quantum, they also have their searching space, complex problem searching space. So they try to break down these problems into the subcategories. So P problem this is known as the searching space. S space is there. So P is the effectively solvable by classical computer. The classical computer, they can solve this type of problem very easily, and so some of the problems that they are not solvable by the classical computer, they can solve by the quantum computer. So quantum computer, they can solve with the help of the quantum machine. So BQP problem, if any one problem is there, then that is they can easily solve with the help of the quantum computer. Of course, classical computer computer can also try to solve and solve, but that means the probability is less, and also the type complexity is very high in that case. And EQB problems, those they are not BQB problems. That is a success problem has a success probability is 100%. So EQB problems are there. So this is the way that how the quantum matrix, how the quantum computer problems can solve. Now, if you have the two hardware, that means the two quantum chips are there, or you can say you also have an account on the IBM, also have the account on the Google platform. With this with the quantum computing, then how we can compare which platform is better and why that is only the better. The second thing is that if you write a program of quantum machine learning, and in that case, we also need to decide that, okay, if you have the two, you use this number of layers or this number of neurons, another one use the different number of layers, different number of neurons. So which matrix we need to compare? Which one is the better? So that we can create results and we can compare with that one. So one is the with respect to the number of qubits. How many that means, so number of qubits in terms of hardware, our focus is that how many number of qubit machine is there. More qubits, better in a better machine. But in terms of the implementation, in terms of program writing, if some program, if a program they require only 4 qubit at the same time, other they require the 6 qubit at the same time. 4 qubit at the same time is better than the 6 qubit at the same time. Even maybe possible 4 qubit at the same time machine takes the 2 times more time as compared to 6 qubit machine, because 6 qubit machine cost and their availability is very challenging as compared to 4 qubit machine. So scalability is that one matrix is there, and so we need to check that whether it is scalable or not. And quality is that means the measure in terms of the quantum volume, that is whatever the size of this one, that is the quality of that one. So how what the size of the information, how much information we fetch, and of course the speed, fast speed is the better option in the quantum computer in that case. So now, what were the algorithms? So in the picture, IBM they proposed the quantum algorithms. Here we have seen that. That I think so. There is a slide is there where this one. So here this quantum software applications and algorithms, quantum algorithms are there, and application models are there. So these quantum algorithms, what these companies are proposed or supposed. So we can easily classify into two categories. One is the pure quantum algorithms. They are using that means the entire quantum computer. They are not using any classical versus quantum. They assume that we have the quantum computer and we can solve the entire problem on that one. Hybrid classical quantum algorithms, they use the pure quantum algorithm with classical components and classical. So that means you can mix two problems. Say for example, if you use the pre-processing, data pre-processing on classical computer and machine learning on the quantum, then we can say this is a complete algorithm is there, only one algorithm is there. Then we can say this is the quantum classical, then a hybrid algorithm, not the pure algorithm in that case. And this is the research direction that various papers come. So we also published one survey paper, and this picture diagram is on that survey paper. So we can easily find out that that means the both direction, pure and hybrid, they have various algorithms, pure quantum algorithms. They have the quantum and Fourier transform. So quantum walk is there, quantum algorithm for linear algebra. These are the pure quantum algorithm. There is no component of the classical computers and other things. You can easily run on that one. And for the hybrid algorithms, they of course hybrid algorithm use the quantum, but quantum is not able to directly takes the input. Then classical algorithms is required in that case. So machine learning usually use the hybrid because of that means if something is quite easy on the classical, why we force on the only to solve the problem on the quantum, why not classical platform. Now we comes to the quantum development toolkit. This is our another section. So if we assume that you are familiar with the quantum algorithms, quantum hardware and other things. So there are two type of the platforms are possible. One is the simulated on the real hardware, or executed on the quantum computing. So suppose one IBM solution is there, and you can run or you can use as a simulator tools of the quantum computer. And this is operations are possible on the normal computer, on the classic, that is this is real computer. we can't this time we can't require the real quantum computer, so you can use that one. This similar, and the result is same, and of course the program is also, once the program is settled down, you can understand, then you need to shift from this one to the that one. So, and these are the three famous quantum simulator. They are widely used in this domain. The one is the state vector simulator, other one is the density matrix simulator, and third one is the tensor network simulator. Tensor network simulator, if we use, and if we try to run on the quantum machine, it takes very less time as compared to this is the normal computer running on the this algorithm. Because uh, that is the quite that means then a complex procedure is there for the algorithm, that tensor algorithm. Now recently some paper comes into the picture, they reduce the dimensions and other things, so simplify the problem of the tensor problem in that case. But these are the three are the quantum simulators are the quite. Now we come to the what platforms are available, or the simulator platforms are available for the quantum machine learning or quantum computers. And one is the, of course, Click is there with the help of this is the Google platform. So Google provide this one, since this is and of course some of these devices. So in the back end they use the quantum machines. You can take the quantum machines in that. Of course, they also provide the simulator. So, and here some up to some processing it's free. So my suggestion is that please note down this simulator and try to create an account or use that one. And this is on the Python language, so it's a quite easy to programming on this one platform. In that case, yeah, some that means the some queries are there from the participant. So let we can take also that queries first, and then we continue. So one is that this query is from where, that is, how can quantum computing toolkit such as this be integrated with the standardized to provide a seamless and user-friendly experience for developing. So standardized that integrated with each other, or integrated with that means the classical computer. Yes. This query is asked from which participant? Can you please?
Pushpalata.
Yeah.
Dr. C. Pushpalata.
So that is that if we in the generic, if we understand that, see, first thing is that integration between these are the different platform. One supporting the Qiskit is IBM platform, also is the this is the Google platform. So it is not possible that we can connect these two things together. Their programming skill is also different. So they are the different platform. Now it's your choice which platform you want to use. So you can use any one of these. But if we talk about the integration with respect to classical to the quantum, then it's integrated, and it's already integrated. That means whatever programs or whatever the part of the program you want to run on the classical computer, and then after you can forward the remaining on the quantum computer. That integration is step-by-step integration is possible, and that is not integration. That means we can see the problem, we can divide into the sub problems, and one first portion of the problem we can solve at the classical, and the second one is the quantum computer. So say for example, machine learning, the data preprocessing and machine learning. So data preprocessing is so on the classical, and other is the quantum. The second query is that under what conditions does the synergy between the quantum and classical computer provide the computational advantage over the purely classical approach. So if the data size is quite large, that means the problem size is quite large, then quantum is of course the best one solution. Hybrid sometime why required, say for example quantum and classical. So quantum, the main limitation of the quantum is their qubits. You can't say that that means the direct information we can say that is the fit for the available machine qubit size. So in that case, first we need to twist the problem, or this data set or the problem statement, so that they are then make them suitable for the available qubits machine on this one. So for how we can make them available, because the problem domain is different, problem comes from the other end. So classical computer responsibility is that they can make them suitable for this one availability of the qubits, and once they convert the problem suitable for the available qubits, then after they can handle in that case. So in that case we can say that quantum alone is not possible, quantum classical is required, both together are required. Classical is not possible because of the speed and because of the size in that case. So let's we continue our ongoing. So this is the Google platform. They provide the platform for the programming. It's very nice and it's very easy. And they are written in the Python programming language. So that means the implementation is also quite easy because of the most of the libraries are already there. And they can handle the noise quantum channels using the Monte Carlo simulators and other tools. So noise they can also handle. So you are not worried about much noise in that case. And now in the simulator tools support all standard gates always at the custom gate. So this is quite interesting that you can make your own gate. So say for example, same operation you need to repeat again and again after a certain time period. So you can make your own gate logic in that case and call that one gate. No, in place of you can write the every time you can write multiple lines there, and so the complexity is very high here. We can make our own gate or customize the gate. Then that is the good one. And now there are three methods are there for using this one simulator. One is the exact simulator. So this is the noiseless. That because this is a simulator tool, there is no noise. That is, you assume that your condition is quite ideal and there is no environmental hazards is there. So you can say that this is the exact simulator. There is no noise. But practically, such results are not useful because anyhow the physics has some noise. So when you run your program on the real quantum machine, then noise comes into the picture. Now, so the second approach, they say that okay, we can inject the noise. That means that they force the noise in your simulator. So this is the noisy simulator, and so this is somehow practical, nearby the practical is there. And the third one is the perimeter shaping, which is circuit is to obtain the optimal perimeter by measuring and changing the perimeters like this one. This is the Qiskit architecture. Here the quantum developer is there. They write a program on a normal computer, not a quantum computer sort of thing. Then after some simulator environment is there. That means UI, UX or IDs are there. They call the Google platform where the machine is there. Then quantum engine call for this one purpose changes in the format and other things. Then quantum computer or quantum simulators based on your choice. You can pick any one of these two, whether you want to work on the quantum simulator or you want to work on the quantum computer. So it depends on you that in which direction you want to work or availability of this one. And this is the Google first that means the chip comes into the picture, that is the 22 qubit is there, and it's quite old is there. And this is the that means the this is not a that means the futuristic. It's already that means available in the market like this one. So but the problem is the 22 qubits. That means you are not able to perform the operation more than 22 qubits. Then they propose another solution of the Google, that is the 72 qubit comes into the picture. 72 is quite large as compared to 22, but not much larger. So definitely you need to go in the other direction. So after that there comes the 54 superconducted qubit system. So they have the multiple. That means they make the grid here. So then they increase the size with the help of gridding, not directly working on that one. And these are the features that are available on the quantum platform. So you can make the quantum in a virtual machine. So VMs you can create, and with the help of VMs you are not required to configuration much or complex configuration in your program. Or QSIM is the quantum simulator tools is there. They simulate up to 14 qubits with the Intel 90 core and other things in that case. This platform, Google platform, their internal architecture support like this one, and machine learning support is there, of course. So this is the CPU, GPU, TPU. Now QPU comes into the picture. Quantum processing unit like this one. And based on this colors, it says that okay, this is the towards the quantum, and this is the traditional or classical whatever they're going on. So we need to put on the both together. So here they have the traditional simulators, or here we use the Qiskit type of the simulator platforms, and they have their libraries are there, operations are there, layers are there, and then after data is there. So they have their own sequences there. Now for IBM also, of course, the previous one, all these things are related to the Google's. Now IBM also work in this direction, and that means propose a platform. So Qiskit is a very well-known platform. That means that here we also most of the time using this one platform. So this is a quite interesting platform is there. This design is a IBM, and they provide all the libraries are there. So you are not worried about the libraries, and charges are also not there. So it's very good that we can use that Qiskit. So we are not required too much worried about how to write the program. There are multiple examples are there. You just drag it down and run the program, then modify somewhere else and other things. And these are the chipset they propose with the help of the IBM. Earlier, these are the that means the Google chipset hardware. So the IBM also proposed 4 5 architecture, and these architecture that is different architecture based on the qubit properties or the size and other things. So some is the small size qubits, some are the large number of qubits are there. And that means these are the comparison with between that, okay, what is the uniqueness in that and what is the uniqueness on other hardware. Qiskit support machine learning libraries. So why people are using? Because they are in all the dimension or directions. So if someone want to machine learning libraries, quantum kernels are there, quantum SVC machine support vector classifier is required, regression is required. So QSVC is there in place of SVC, support vector regression or classification. They support the QSVC. So you can directly call this library and use the quantum libraries. And this is they also support the libraries with respect to the physics, chemistry, and biology. That means whatever the nature related problems, they have all these supports and the libraries. Financially, they also propose this is monocular simulators and other things to solve the financial problem, and optimization condition, gradient descent, and other things. So that libraries are also there. So with the help of this, we are not worried about libraries, or we are not required to start from the scratch or think about that how to solve the problem. Okay. Now these are the IBM quantum simulators. So that means based on the size, based on the processing and algorithms, they propose a different simulators tools and with the. But what's happened that it's very fastly people are changing. That means this that is maybe possible in 2025 or 24 something is different now, and next year 26 something is different because the changes are quite fast. So suppose that 127 qubit processor is this one. If this size of the processor 500 qubits comes into the picture, the change, huge changes are required in the simulator tool, because that libraries are not required. Better libraries are possible. They can perform the multiple operation at the same time. So here we can't say these simulators are right now. Maybe possible there are changes are there, but of course the phenomena how to use that it's the same. So these are the chipsets are the IBM chipset, different from the previous one Google chipset. So 2019 comes into the picture, uh, and 2022 the other comes into the picture. 2021 every year they published the design of a new architecture and engage, so that they can increase the qubits information in that case. So this is the pictorial diagram is there, that okay, how much number of different type of the computers are proposed by the IBM timely. So now we are just so that okay, we have published 2 papers in this direction. They're both are in the archive. So the main focus in the papers are that one is of course this whatever we are talking in this lecture, that is there. Another one is that how federated learning machine learning make them suitable for the quantum federated learning machine learning. So if anyone is working on the federated learning or the quantum machine learning, definitely they can see this one. So here the objective is that suppose your problem is quite complex and you are using servers or more than one server, and these servers are the quantum machines are there. Those they are integrated, they find out the result and share this result to the different. So one is possible that okay, one federated learning server is there, other one is the multi federated learning servers are there. And when we integrate and when we can do the averaging and other things, practically we assume that there is no error, no noise is there. Here the noise problem, no, quantum has the noise problem. So in that case, and there are 2 problems. One is of course the noise problem in that case. Another problem is that the qubit size. So assume that the architecture is quite big, and this bottom or the leaf devices, they that means they forwarded the trend model to the upper one or download the trend model and like this one. But your machine is not support that level of the qubits. You can't work on that machine. So in this problem, what is the objective is that you need how to select a effective machine. So when we have the account of IBM or this Google platform, you can see the multiple machines are there, and you can use the limited machine. You need to pay the cost of that machine. So if you are required 64 qubit, why you have the 128 qubit machine? So better you can select the 64 qubit, but the 64 qubit machine has the noisy, they have the noise level is very high. So we need to decide that, okay, up to what level of the noise we can tolerate, and if we tolerate this level of the noise, what additional cost we need to pay, cost in terms of the revenue, in terms of the accuracy in that case. So suppose if you want to write a one program, so one first thing you need to, and problem statement you need to think, then after you need to draw the circuit, then after you need to find out the platform, execute the result on the platform, then after result, whatever the result is there, you need to analyze and set the result and transmit that result to the end user. So this is the way that quantum development life cycle work in that case. This is a toy example, very first example. Whenever you go to the how to do the programming of quantum, you can find out the hello world example. So in this hello world example, that means suppose you want to want to perform some operations. So this is, assume that you want to perform this type of operations. So very first you need to make the circuit, and input is there. This is the measurement unit. After measurement you can find out these results 0 and 1. So this is a measurement gate is there, this is the S gate, and the X gate is there. So these two inputs are there, 0 and 1. Play with this information and measure the information, and this is the result. So this is the first program is there, and this is the that is the platform, Qiskit platform. How we can write the program? These are the your inputs. Before calling the input, you need to call the libraries, because you are using a various gates are there, measurement units are there, inverse is there. So all these are the libraries are there. You need to call the functions and other things from these libraries. And here you need to initialize this Q0, Q1, or that is the registers and other things. Then after you use the quantum circuit we already draw this one quantum circuit here, and you need to write this type of program. Then after measurement, and finally you can see the result. So this is all about the exam says that, okay, what is the accuracy when you predict the 0 or 1, like this one. Yeah, so that means quite simple, very simple. And if you see that, okay, it's not a complex, that is the very straightforward way is there. So here very first you need to have a problem. Once the problem is defined, say for example image classification problem is that, and we want to use the SV and C support vector classifier. So here so just so here the library is already there. So Qiskit already have the library, so you are not worried about that from the sketch we need to write. So draw the circuit call the libraries, then execute, and then after see the result. So we need to draw the circuit. So whatever the logics are there, gates are there, we need to implement that one in the program and see the result. Once you run this one, you can find out the accuracy that, okay, this level of so suppose black and white. So these are the blacks and these are the white coins are there. With the help of this one, you can very easily predict and find out that one. This is another example for this one, that how we can write the same program in a different fashion and different way. But of course, that means the programming language is very simple, straightforward. You need to call the very first you need to call the libraries, then after variables, then perform the operations and see the results. And one interesting thing is that this depends on the platform and platform. That means the result accuracy also depend on the platform. Why this difference is there? Because of only the noise. Noise is the main problem in the quantum. So people try to reduce the noise, because if noise is there, then you're not able to find out the correct result and whatever the result you are expecting in that direction. So this is all about from my side. Thank you very much for all the participants, those they are listening here. Now this is the right time to take the queries. Yes, anyone? What are the key advantage of the Qiskit to get set? So there is no advantage or disadvantage. It's depend on your platform, which platform you are using, and what. Say for example, someone says that, okay, I want to use the two gates in place of one complex gate, or someone says that I can design or and that means our custom gates. So custom gates is very helpful. That means why it's very helpful, because of you can make your logic complex logic in a one gate, but its complexity is high as compared to the inbuilt traditional gates. So similar as that one, we can't say which one is better. It depends on your that means the application and your scenario in that case. Can we able to install quantum in the Google Colab Jupyter notebook? No, that means as of now, my experience is that one you can that means the Google give a platform and you can use that platform. So you really feel that, okay, what is, because they are not able to provide the noise level and other things. Otherwise, what's happened that you forcefully you can say that, okay, this 0.01% of the noise of my result. Why? They automatically have the noise libraries and other things. So real feeling of the hardware platform you can find out only when you can create your account and using that one. That is there. Practical limitation, the next query is the practical limitation of this technology on the current hardware. That is the if you talk about the quantum hardware, then that environment requirement is very high, because quantum, they can lose their property if their environment changes. This is a quantum physics, so think about that, what temperature is required, what power is required. Huge machine, bigger size of, then a heavy power is required, so that you can generate the quantum physics in that case. And also maintaining the state in terms of the temperatures and other things are the classical. That material requirement is very high. So anyhow, right now it is not a possible that that is put the quantum machine everywhere. Of course, might be possible after 5-10 years when this is material science and other things comes in an advanced stage. Then that is the possibility. But right now, the hardware, that means the material requirement hardware is very high, and that is the main challenge in that case. Yes, so this is where we can get, yeah, thank you. Can we use Jupyter Notebook? Yes. So I think so we have taken all the queries. So any other queries, please ask. Yeah. So this is all about from my side. Yeah. Thank you. Thank you very much. Yeah.
Thank you, sir.
Yes, please.
On behalf of Karunya Institute of Technology and Sciences, I extend my heartfelt gratitude for your enlightening session. Your clear explanation on all the topics provided a comprehensive understanding of this evolving quantum computing field. Thank you, sir, for making this last session is also more informative. Thank you for sharing your expertise and time in spite of your busy schedule. Thank you so much, sir. Thanks a lot.
Thank you very much for organizing this wonderful event, inviting me, and thank you for all the participants, those they are attending and listening. And if anyone has any point, any queries, or want to discuss, want to any joint work or collaboration work in this in this domain, definitely they can mail us, and we will communicate with that one. Yeah, thank you very much. Thank you.
Thank you, sir. You can disconnect. Thank you. Participants, kindly stay back. 5 o'clock, the exam link will be posted here, and you can take your exams from 5 to 6. So kindly stay back. Feedback form, you will get it at the end of the valedictory section. Valedictory session will start at 6 p.m. So 6 to 6:15, after the end of valedictory session only, feedback link will be posted. Kindly stay back here. 5 o'clock sharp, the exam link will be posted here. Thank you. I hope you all have gone through the materials that I have shared with you in the mail as well as in the WhatsApp group as per your request. A few of the recordings we have shared with you. Few other recordings also will share with you by tomorrow, so you can use it. Can we join 5? Yes. You can take a break and you can join at 5 o'clock here. Thank you. 5 o'clock sharp, the link will be posted here. You can join at 5 o'clock. Thank you. Okay. Not in ATAL portal. The link I will share, in that link only you have to give your exam. It's a Google form based test. It's an MCQ test. So you no need to go to ATAL platform. So from here itself, the straight link will be posted. Yeah, it's up to you. 5 to 6 o'clock, the exam time. You can take the exam based on your convenience. The questions are 30 questions, 30 marks. Sir, we have to, there is a time limit for everything. So we have to finish it and then we have to start the valedictory. After that, your attendance will be posted. With that, okay, we have to close this 6th day program. Yes, recorded sessions are already, I have added inside the Google document itself. Today's attendance link you will receive at the end of valedictory session. Yeah, you can close your ATAL portal. No need to go there. Today, any feedback? Yeah, feedback is there. Feedback is going to be considered as your attendance. Also, you can give your voice feedback. Prashant Parthasarathi or somebody. Any doubts? Parthasarathi ma'am or sir, do you have any doubts? You have raised your hand. Thank you so much. We can.
Good evening, madam.
Yes, sir. Good evening, sir. Please.
Yeah, the certificates we need to download from ATAL, or that also you will send it to us?
ATAL. That instruction will give you at the valedictory session time, sir.
Okay, fine. Thank you.
After giving the exam, we have to update your attendance and marks in the ATAL portal. Then only the feedback option will be enabled for you from your end to enter in the ATAL portal. Then only you can able to download. ATAL portal also you have to give you feedback. Then only you can able to download the certificate. So that we have an instruction like don't leave from the WhatsApp group. Once we have updated everything in the ATAL portal, within 3 to 4 days, we'll inform you back. Because the strength of the...
Now we have 10 minutes time. So can we give feedback in ATAL, madam, now?
Sir, ATAL, once we have updated your attendance, then you can go for your feedback.
Okay, fine. Thank you. Thank you.
Okay. No need to go to ATAL portal. From here itself, the link will be posted and you have to take the test from here. The exam link is posted. You can take your test now. Finish your exam and join again for the valedictory session. After that, there is a feedback form for today's attendance. I will post the same instruction in the WhatsApp group. But the link will not be posted over there. If you're not able to open the link, just copy paste this link and paste it in the browser, any one browser. If you paste it and just press the enter button, you can able to open this form. It's just like a normal Google form, how you will fill the same way the questions are available. You choose the right option. And don't forget to click the submit button at last. You have to click the submit button, then only the answers will be recorded and it will be submitted. You can just click on this link and the exam link will be open. You can able to see the questions, or otherwise you copy paste this link in any one browser and just click enter. The form will be open. You can able to see the questions. Each question there is only one right answer. Choose that option and complete all the questions and then click the submit button. Then only your answers will be submitted. No, for attendance, it is separate. Attendance will be collected at the end of valedictory session. So after 6 o'clock, you have to join for valedictory session. So end of valedictory session, you will get your attendance link. This exam is not going to be counted for your attendance, so you have to join for valedictory session. This is how I posted in the WhatsApp group as well. If you have any doubts, you just post this. If you have any doubts, post your queries in the chat box. Please share me link. Okay. Certificates you have to download from the ATAL portal. Once we entered all the details about you, your marks and attendance, then we will communicate in the WhatsApp group. After that, you can go to ATAL portal and you can able to download. Participants ID, you check the email communication that you have received from me in the first mail, first time in your email that you have received a communication about this webinar link. In the same mail, this participant ID is attached. So far, you also have marked your attendance using the participant ID. So the same ID only you have to enter here also in this exam page. After completing the test, you can leave, but join here in the same meeting at 6 o'clock. After completing the after completing the exam, you can leave from this meeting and you can join at 6 o'clock for validity session, followed by your attendance. Thank you. Yes. Once you have completed the exam, you can leave from this meeting, join back at 6 o'clock for validity session to fill your feedback form. Thank you. If you are late also, there is no problem. Please take your exam now. After finishing this exam, you can leave from this link and join back at 6 o'clock for validity session. If you have completed, you can leave from this link and join at 6 o'clock for validity session. Or if you want to stay back here, you can stay back in the same link. I appreciate all of you who have completed the exam on time. Thank you. Thank you, professors. You can give your exam and it will be published in the ATAL portal. The result will be published in the ATAL portal. This is the final exam. No need to do any exams in the ATAL portal. This is the final exam. There is only one exam. This is the exam. There is no need to do any exam in the ATAL portal. After we marked your attendance and the marks and the feedback entry, everything in the ATAL portal, then the link will be available for you to download. So it may take 3 to 4 days. So stay back in the WhatsApp group for further communication from our end. Once we finished all the tasks from our side, then you can download. So downloading part of your certificate, that time you have to go to ATAL website and you have to download from there. There they will ask a small feedback about this FDP. You give your feedback and then you have to download from there. But for 6th day attendance, today's attendance, kindly wait. After valedictory session, the attendance link will be shared for you. So kindly come and join here after 6 o'clock. Or you can stay back in the same link. 6 p.m. will start the valedictory session. Let all others complete their exam. Thank you all for those who have completed their exams on time. Thank you, professors. After attending this test, if you have completed, please come back and join for valedictory function at 6 o'clock in the same link. After that, after the valedictory session, you have a feedback form filling part that will be counted for today's attendance. Feedback on ATAL portal, you have to fill it later, after 3 to 4 days. After that, only you have to enter, not now. So the feedback form for day 6 will be shared at the end of valedictory function. Course will be updated later. If you have completed exam, you can take a break and join back here at 6 o'clock for valedictory function followed by your daily attendance. Kindly stay back for validity function to give your thanks note through your voice. I'll enable mic option. At the time, you can give your thankful note through the mic. So kindly come back, get ready and come back for validity session. Yesterday attendance will not be given here. Today only, now the test link is posted here. Today's feedback form will be shared to you after the end of validity section. Those who have joined now, maybe you may not attended any session. If you have taken the exam, but attendance is also mandatory, you have to maintain 80% minimum attendance, otherwise you will not get the certificate. So 80% minimum attendance and 70% marks, these two are mandatory for getting your certificates. Kindly join at 8, kindly join in the same link at 6 p.m. for valedictory function. We have 5 more minutes to close the exam link. Exam link will be closed at 5 more minutes. 6 o'clock sharp, it will be closed. So 5 more minutes are there. The marks will not be reflected immediately. It will take 3 to 4 days time. It's a manual entry. It will take another 3 to 4 days time, sir, for processing all your attendance and marks. Then once we entered, it will be reflected there, and you have to give your feedback in the ATAL portal and for downloading your certificates at that time. So that's why we are saying, please don't quit from WhatsApp group, stay back. Once we have done from our end, we'll inform you in the WhatsApp group. So at that time you can join, you can log in ATAL portal for downloading a certificate. Only stay back for further instructions. Once we update from our end marks and everything, then what you can able to download the certificate. So we'll intimate you through mail or WhatsApp group as well. We have to check the score. So everything will be reflected in ATAL portal within 3 to 4 days time. So kindly stay back. We'll update you through mail and WhatsApp to check your attendance and marks in the ATAL portal. Certificate you have to download from the ATAL portal only. By default, maybe it will be in absent or present. Okay, well, we will update it. Don't post your ID number here. Kindly stay back. Free attendance and feedback link will be shared at the end of valedictory session. Don't post your ID numbers here. Imran, sir? Sir, are you available?
Yes, ma'am.
sir.
Yes, ma'am. I'm available, ma'am.
Okay. We'll start the valedictory session. Good evening, everyone. It's my pleasure to welcome you all for the valedictory session of AACT sponsored ATAL Faculty Development Program on Quantum Computing, organized by the Division of Artificial Intelligence and Machine Learning, Karunya Institute of Technology and Sciences, Coimbatore. The 6-day program, held from February 10 to 15, 2025, has been an enriching experience, bringing together industry experts, researchers, and faculty members to explore the fascinating world of quantum computing. As we conclude this journey, let us take a moment to reflect on the knowledge shared, the discussion held, and the collaboration fostered. I sincerely appreciate the participation and enthusiasm of each one of you in making this program success. We are honored to have with us Dr. Emmanuel John Raja, Head of the Division of Computer Science and Engineering, who has joined with us to deliver the felicitation address. Sir, we kindly invite you to take over the session.
Sure, ma'am. Thank you, Jemima, ma'am, for hosting me. Am I audible and visible,
Audible,
ma'am?
audible. Yes, sir. Yes, sir. Everything's fine.
All right, all right. Thank you so much. So this is a long journey, 6 days continuously. I could understand after the regular class hours, majority of the faculty members, the facilitators are able to join this AICT sponsored online ATAL FTP on quantum computing. Started on 10th of February and is concluding today. At this moment, it's my privilege to be part of this. So thankful to Dr. Jemima for welcoming, for inviting me. And I'm also thankful to the administration and management of Karunya Institute of Technology and Sciences for giving all the support and the facilities to conduct this ATAL FDP. At this moment, I also remember Dr. Dinesh Peter, who is the coordinator for this workshop. And it's my duty to recognize and uh, probably thank the Atal Academy for accepting the invitation from Karunya Institute of Technology and Sciences and then permitting us and supporting us, sponsoring us to conduct this mega event. Continuously sitting for 3 hours every day for 6 days is really a Herculean and mammoth task, but you all have done it. Thanks to all the resource persons who are part of this FDP. Probably we have got a host of people from a strong academic and industry background from the premier institutions. I would like to acknowledge Dr. Sandeep Kumar Singh from IIT Roorkee, who joined this FDP, and also Dr. Monica Agarwal from IIT Delhi, part of this FDP as the resource person. Then Dr. Hari Pratap Gupta from IIT Bhubaneswar, Varanasi, and also Dr. Saravana Kumar from Bosch Software Global Technologies India for sharing their expertise. We also had Mr. Karthik Ganesh Durai from India, then Anupam Biswas from IIT Silchar, and then Dr. Arvind Vishnu from Amrita Vishwa Vidyapeetham, India, Dr. S.P. Raj Manohana from Pondicherry University, India, who have shared their expertise during the last 5 or 6 days. And it's my privilege and thank once again Dr. Jemima for hosting this event with the support of Dr. Ebenezer Jangam, who is the co-coordinator and also the professor in the Department of Artificial Intelligence and Machine Learning of Karunya Institute of Technology and Sciences. I'm sure these 5-6 days have been fruitful, enriching your skill set and knowledge in the areas of quantum computing, which is one of the emerging technologies now. The Department of AIML is also planning, if I'm right, to establish a specific center for speeding up the research and also bring out a lot of groundbreaking technologies in the areas of quantum computing with us, in addition to the quantum machine learning and quantum cryptography and so on. So with this note, I would like to appreciate every one of you for being part of this FDP continuously. I'm sure we have done the justice and we were able to give you adequate skill set and the knowledge on these 6 days of FTP. So wish the team, participants, audience, all the resource person, all the very success for a continuous growth in the areas of quantum computing. Thank you, Jemima ma'am, once again. Have a great evening.
Thank you, sir. Thank you, sir. We can discuss.
Thank you. Thank you.
Since they're going for meeting, right? Okay, then, thank you.
Yes, ma'am. Yes,
Uh,
ma'am. Yes.
Yes, sir. Thank you. At this juncture, it's my responsibility to thank Karunya Institute of Technology and Sciences and ATAL Academy. I would like to express my heartfelt gratitude to our Chancellor, Vice Chancellor, Pro Vice Chancellor, and Registrar for their unwavering support in this for successfully hosting this faculty development program. Their encouragement and guidance have been instrumental in making this event a grand success. I would like to extend thanks to Athletics Academy for accepting a proposal and conducting this event and sponsoring for this event. I would like to express my thanks to Dr. Dinesh Peter, Head of AML, and Dr. Emmanuel John Raja, Head of Division of CSC, and Dr. Ebenezer Jangam, Coordinator of AML, for their valuable support towards the success of this program. I would like to thank the following resource persons for their wonderful lectures with us. I hope all you also acknowledge the same. Dr. S.P. Rajabhogana from Pondicherry University, Dr. Saravana Kumar from Bosch, and Dr. Karthikanesh Durai from Quantum Research Lab, and Dr. Arvind Vishnu from Amrita, and Dr. Monica Agarwal from IIT Delhi, Dr. Hari Prabhat from IIT Varanasi, Dr. Anupam Biswas from NIT Silchar, and Dr. Sandeep Kumar Singh from IIT Roorkee. I hope you all have got enough inputs from all these 8 resource persons in this ATAL FDP. They have covered the following topics. I hope you also witness the same: quantum mathematics, quantum computational implementations and application, demonstration of QML model and Qiskit, and quantum image processing, quantum machine learning for social media network analysis, quantum computing toolkit for nuts and bolts to stack of tools, all the basics he has covered, and cryptography in the quantum world, exploration of quantum AI. I hope most of the areas related to the quantum computings are covered in this FDP. I extend my heartfelt thanks to all the faculty members and research scholars, PG scholars from AICT approved institutions and industry personnel who have actively participated throughout the program despite your busy schedules. I truly appreciate the effort and the dedication you have shown in attending this session and coordinating with us. Your commitment to learning and engagement, even amidst your professional and academic responsibility. With this, I want to I conclude my vote of thanks. Thank you all once again for your valuable time and participation. Now we would like to hear your feedback and share your thoughts. If you raise your hand, I'll enable you to speak. 1 or 2 feedbacks we want to hear from you. Yes, Sandeep sir. Yes, I have enabled. Professor, you can speak. Or if you want to post your feedback about us or about this event and about the resource person and Kalai Selvi, ma'am. Yes. Ma'am, you are enabled. You can talk. Whoever raised their hand, I'm just allow them to speak. Please unmute yourself and talk.
So I am Dr. P.C. Kali Silvi, Professor and HOD, EC Department at Excel Engineering Colleges, Komarapalayam, Namakkal District. So it is a very good session, and thank you for introducing us to the renowned resource persons through Jemmy ma'am. And all the sessions started well ahead in time, and all the informations were passed through WhatsApp as well as through email, and we felt very comfortable from day one to this present session. And each and every session was well packed with the introduction part up to the feedback sessions, and it was very good experience for all of us here. And I thank the organizers, I thank Karunya University, I thank AICT for giving us this wonderful opportunity to interact with the resource persons all around India and abroad. And It was a very well planned and well executed session, ma'am. Thank you for this opportunity.
Thank you, Dr. Kaleselvi, ma'am. Nice to hear from you. Really, it's a more encouraging words for us to post and focus on other events as well. Thank you.
Welcome, ma'am.
Thank you. Harshita, ma'am. Harshita, Professor Harshita, Deepa. I have enabled. Yes, please proceed.
Hello, ma'am. Good evening.
Good evening, ma'am.
Yes, ma'am, the entire sessions that every day that we had, literally, I was zero in this, the particular topics and all. So each and every resource person has given they have explained very nicely, and really, this FDP was very, means it has become very useful for me, and definitely it has ignited interest for that particular topic. And now I'm thinking to work more over it. And since you have given the contacts of various resource person, ma'ams and sir, so if further if I will be needing some kind of guidance, I will definitely approach them. So ultimately, that was means it proved to be a very good and amazing FDP for me.
Thank you, ma'am. Thank you for sharing your inputs. Professor Deepa and Professor Shanti, Professor Nirmala, kindly unmute from your end. You can talk one by one.
Good evening, ma'am.
Good evening,
This
ma'am.
is Deepa, Associate Professor, Department of CSC from Panimalan Engineering College. Actually, all the 6 days were we felt very comfortable, mainly because of the timings. So when it was during the day hours, we would have felt it very difficult to attend the FDP as well as manage our duty hours. And this time was very comfortable. And we are able to gain a lot of insight about quantum computing. Now I wonder, I should have started my research at this time after knowing about quantum computing so that I would have enriched all my experiences. And all the sessions were very informative. And thank you so much to all the organizers as well as the resource persons. Thank you so much, ma'am. And we expect a lot like this from your side. Thank you all.
Yes, ma'am. Thank you so much for your feedback.
Hello, ma'am. Myself, Nirmala Gandge from
Good
KLS
evening, ma'am.
VIT, Haryal, ma'am. So the session's really good, ma'am. Only yesterday I didn't attend it because there was a function in our college. So if possible, please send us yesterday's video. And other days, all days I attended. All the whatever the lecturers are well explained in very whatever the topics. They covered everything. And in the beginning, I was confused to which subject I need to search for the research. But now, after attending this FDP, better quantum computing is better for the research. I think so. Thank you, ma'am. Thank you very much.
Thank you, Nirmala, ma'am. We have posted all the videos in the Google Drive, and some of the days videos I didn't upload because of my bandwidth problem at home. Definitely, Monday you can able to see all the links in the chat drive.
Okay, thank you, ma'am. Thank you.
Thank you. Deepa, ma'am, Shanti, ma'am. Ma'am, you have to, okay, down. Yes. You have to unmute from your end and you have to talk. I have enabled the option. If you want, those who want to give your feedback, you can click on the raise hand option. I'll unmute and then you can talk. No problem. Or whichever comments you want to post it, whether it is positive or negative, no problem. Please post it in the chat box. We'll work on it. Thank you. But I'm also personally receiving lots of messages and calls from your end. Thank you. Any other feedbacks? Shanti ma'am, you can proceed. Okay. Okay, so shall we wind up the feedback session? Small instructions, the final instructions for you. E-certificates will be issued by ATAL Academy to the participants who have attended the program with the minimum at 80% attendance and minimum 70% marks in the test. These two things will be entered by us and it will be reflected in the ATAL portal. Will take time for processing these details within 3 to 4, but at the earliest we'll try. So kindly wait, and once it is uploaded, you can able to fill your feedback, and then you can download download your certificate from the ATAL portal. So do not exit from this WhatsApp group until the process is completed. When we finished from our end, we'll inform you through the WhatsApp group as well as through the Gmail. After that, you can download from the ATAL portal. So after that, you can able to check your marks as well as attendance in the ATAL portal. So kindly wait for 3 to 4 days time. Now, day 6 attendance I have posted. So kindly fill the feedback form for day 6 attendance and feedback. With this, we'll wind up this FDP. Thank you all. Thank you, participants. Now you can, after marking your attendance, you can leave. Thank you. Thank you all. Thank you, Jangam sir.
Thank you.
Thank you, sir. After marking attendance, you can leave.